You are not moving through time. Time is moving through you, and everything your brain has been telling you about reality since the day you were born is wrong. Right now, in this exact moment, you think the past is gone. You think the future hasn't happened yet. You think there is a single shared now unfolding across the universe like a perfectly synchronized clock. Isaac Newton thought so too. For 200 years, the greatest minds in physics thought so. They built telescopes, calculated orbits, predicted eclipses, and split atoms, all while assuming that time ticked forward at the same rate everywhere, for everyone, no exceptions. And then a 26-year-old patent clerk in Switzerland picked up a pencil and destroyed that entire framework in a single year. What Albert Einstein discovered in 1905 wasn't just a new equation. It was a betrayal of human intuition so complete that even today, more than a century later, your brain refuses to accept it. He proved that time bends, that it stretches and compresses depending on how fast you move and how deep you sit in gravity's well. He proved that the past, present, and future do not exist the way you experience them. And he proved it so convincingly that we now rely on his predictions every single day just to make GPS work. Without adjusting for the 38 microseconds of time dilation that satellites experience daily, your navigation would be off by miles. But that was just the beginning. Because if time is relative, if space curves, if the speed of light is the one universal law nothing can break, then what are space and time actually made of? Are they real, or are they just illusions your senses constructed to help you survive long enough to reproduce? And if the universe is 13.8 billion years old, does that mean the Big Bang is in the past, or is it still happening right now, in a dimension your mind cannot touch? This is that story. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. For 218 years, humanity believed it had solved the universe. The solution was elegant, complete, and comfortable. Space was a stage, time was a metronome. And everything that happened, every motion, every collision, every sunrise, every heartbeat, played out according to rules laid down in a single book published in 1687. The book was called Philosophia Naturalis Principia Mathematica, the mathematical principles of natural philosophy. The author was Isaac Newton, and what he wrote in those pages became the foundation of physics for longer than the United States has existed as a country. Newton's model was simple in the way that profound ideas often are. Space, he said, was absolute. It was an invisible, immovable grid stretching infinitely in all directions, a container for the universe, fixed, unchanging. You could fill it with planets and stars and falling apples, but the space itself didn't care. It just sat there, a perfect passive stage on which the drama of existence unfolded. Time was absolute too. It flowed uniformly, steadily, the same for everyone, everywhere, at every moment, a cosmic clock ticking in the background of reality. Whether you were standing still or racing across the countryside on horseback, whether you were on Earth or orbiting Jupiter, time passed at the same rate. 1 second for you was 1 second for me, was 1 second for a distant star. This wasn't controversial, it was common sense. It matched what people saw every day. Objects moved through space. Time moved forward. The two were completely separate. Space was the where, time was the when, and neither one cared about the other. The beauty of Newton's framework was that it worked, not just philosophically, mathematically. His laws of motion and gravity could predict the orbit of the moon, the trajectory of a cannonball, the swing of a pendulum, Astronomers used his equations to chart the paths of comets decades before they arrived. Engineers used them to build bridges and calculate loads. Newton's universe was a machine, and if you understood the rules, you could predict exactly how every piece would move. For 2 centuries, nobody found a crack in it. But before we get to the cracks, before we talk about the man who brought the whole thing down, you need to understand just how solid Newton's foundation felt, because the reason his model lasted so long wasn't just that it was mathematically elegant, it was that it felt true. It aligned with human intuition in a way that almost nothing in modern physics does. Stand still right now. Go ahead. Just stop moving. You are, by every measure your body can perceive, stationary. The floor beneath you isn't moving. The walls around you aren't drifting. You are here, fixed, anchored to a spot in space. That feeling, that sense of being in one place, is the core of Newton's absolute space. There is a real, objective location where you are standing, not relative to something else, not dependent on perspective. You are here, period. And if you move, you are changing your position within that fixed, invisible grid. Newton called it the sensorium of God, a frame of reference that existed independent of anything inside it. The ultimate coordinate system. You could rotate the entire universe, spin every star and planet and galaxy in unison, and absolute space would remain unmoved beneath it all, a silent witness to the motion. Time worked the same way. 1 second ticked by, then another, then another. It didn't speed up when you were busy, or slow down when you were bored. It didn't care whether you were moving or sitting still. The flow of time was universal, absolute. The same second that passed for you passed for everyone else in the universe simultaneously. Newton wrote it plainly. Absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external. Translation: time doesn't give a damn what you're doing, it just keeps going. This idea, this separation of space and time into 2 independent, absolute entities, became the bedrock of physics. It was taught in every university. It was assumed in every experiment. It was baked into the language scientists used to describe motion, force, energy, everything. And it made perfect sense because it described the world people actually lived in. Throw a ball. It moves through space. The space doesn't move with it. The ball changes position. Space stays put. Measure how long the ball takes to hit the ground. That duration is the same whether you're standing still or running. Time doesn't shift, it just ticks. That's Newtonian physics. Objects move through space. Events happen in time. Space and time are the stage and the clock. Separate, absolute, unshakable. But there was a subtlety in Newton's framework that's easy to miss. While space and time themselves were absolute, motion was relative. This idea goes back further than Newton. Galileo Galilei figured it out in the early 1600s. He pointed out that if you're standing on the deck of a ship moving smoothly across calm water, you can't tell you're moving just by doing experiments below deck. Drop a ball and it falls straight down relative to you. Toss it to a friend and it behaves exactly the same as it would on land. The laws of mechanics don't change. From your perspective on the ship, you're at rest. From the perspective of someone standing on the shore, you're moving. Both perspectives are valid. Neither one is more correct than the other. Motion, Galileo realized, is relative. What matters is how fast you're moving compared to something else, not your absolute speed through space. Newton absorbed this into his system. It's called Galilean relativity. The laws of motion are the same in any reference frame moving at constant velocity. If you're in a train car gliding smoothly down the tracks and you can't see outside, there's no experiment you can do inside that car to tell whether you're moving or sitting still. You could be stationary. You could be rolling along at 100 kilometers per hour. The physics inside the car would be identical. This seems obvious now, but it was a profound insight. It meant that while space itself was absolute, your motion through it wasn't special. There was no preferred state of rest. You couldn't point to one spot in the universe and say, this is truly stationary. Everything was moving relative to something else. Except there was a problem lurking in this framework, a problem nobody saw coming until the 1800s, and it had to do with light. By the mid-19th century, physicists had figured out that light was a wave, not a particle, a wave. James Clerk Maxwell had written down a set of equations that described how electric and magnetic fields rippled through space, and when he calculated the speed of those ripples, he got a very specific number, roughly 300,000 kilometers per second, that matched the measured speed of light perfectly. Maxwell's equations didn't just describe electricity and magnetism, they described light itself. Light was an electromagnetic wave, but here's the thing, waves need a medium. Water waves travel through water, sound waves travel through air. If light was a wave, what was it waving through? Space, according to Newton, was empty, a void. There was nothing there for light to ripple through. So physicists invented something. They called it the luminiferous ether. The ether was supposed to be an invisible substance filling all of space. Perfectly transparent, completely undetectable except for one thing. It allowed light to propagate. Light waves were vibrations in the ether, the same way sound waves were vibrations in air. This wasn't a fringe idea. This was mainstream physics. The ether was treated as a real physical substance. Scientists debated its properties. How stiff was it? How dense? Could it be compressed? Did it drag along with moving objects or stay perfectly still? Most assumed it stayed still. The ether, they thought, defined absolute rest. It was the one thing in the universe that truly wasn't moving. If you could measure your motion relative to the ether, you'd know your absolute velocity through space. This was exciting. It meant that Galilean relativity, the idea that all constant motion was equivalent, might have a limit. You couldn't tell if you were moving by doing mechanical experiments, sure, but maybe, just maybe, you could tell by measuring the speed of light. Here's the logic. If you're moving through the ether, light should behave differently depending on which direction you're moving. If you're moving toward the source of the light, you're moving into the oncoming wave, so the light should appear to travel faster relative to you. If you're moving away from the source, you're running away from the wave, so the light should appear slower. Think of it like running through rain. If you run forward, the rain seems to hit you faster. If you run backward, it seems slower. Same rain. Different experience depending on your motion through it. If light worked the same way, you could measure the speed of light in different directions and figure out how fast you were moving through the ether. You could find absolute rest. In 1887, two American physicists, Albert Michelson and Edward Morley, set out to do exactly that. They built an instrument called an interferometer, a device so sensitive it could detect tiny differences in the speed of light traveling along two perpendicular paths. The idea was simple. Earth is moving through space as it orbits the sun. If the ether is stationary, Earth must be plowing through it at about 30 kilometers per second. That motion should create an ether wind, a detectable current in the ether that would affect the speed of light depending on which direction you measured it. Michelson and Morley expected to see a clear signal, a difference in the speed of light depending on whether it was traveling along Earth's direction of motion or perpendicular to it. They ran the experiment. They measured carefully. They checked their instruments. They ran it again. They found nothing, no difference, no ether wind, no signal at all. The speed of light was the same in every direction, no matter how the apparatus was oriented, no matter what time of year they ran the test. It was as if Earth wasn't moving through the ether at all, or as if the ether didn't exist. For a while, physicists tried to patch the problem. Maybe the ether was dragged along with Earth. Maybe the measuring instruments contracted in the direction of motion in just the right way to hide the effect. Maybe the experiment was flawed, but the results kept coming back the same. The speed of light didn't change, not with direction, not with Earth's motion, not with anything. Something was wrong. Either the ether was far stranger than anyone imagined, or the entire framework was broken. Newton's universe, the fixed stage, the absolute clock, the ether filling the void, all of it rested on the assumption that space and time were separate, independent and absolute. That assumption had worked for 200 years. It had predicted eclipses and explained tides and launched the Industrial Revolution. But now, at the edge of the 20th century, there was a crack, a small one, easy to ignore, easy to dismiss as an experimental quirk or a measurement problem. It wasn't. The man who would widen that crack into a chasm wasn't a university professor. He wasn't a member of the scientific establishment. He wasn't even working in a lab. He was a 26-year-old patent clerk in Bern, Switzerland. And in 1905, he was about to publish a paper that would rewrite the rules of reality. The patent clerk's name was Albert Einstein, and in 1905, while the rest of the physics community was still trying to figure out what went wrong with the ether, he was sitting at his desk in Bern, writing a paper that would make the whole question irrelevant. Einstein didn't set out to destroy Newton's universe. He set out to solve a puzzle that had been bothering him since he was 16. He'd been thinking about light. Specifically, he'd been thinking about what it would look like if you could catch up to a beam of light and ride alongside it like a cyclist drafting behind another rider. According to classical physics, if you moved fast enough, you should be able to match the speed of light. And if you did, the light wave should appear frozen relative to you, the way a wave in the ocean looks stationary if you're moving at exactly the same speed. A stationary electromagnetic wave hanging in space, oscillating in place but not moving forward. Einstein couldn't make sense of that. Maxwell's equations, the ones that described how light worked, didn't allow for stationary waves of light. The equations only made sense if the wave was moving. If you tried to plug in a speed of 0 for light, the math broke. The wave stopped being a wave. It stopped being anything. So Einstein had a choice. Either Maxwell's equations were wrong or something else was, and Maxwell's equations worked too well to be wrong. They'd predicted the existence of radio waves before anyone detected them. They'd unified electricity and magnetism into a single, elegant framework. They were, by every test anyone had thrown at them, correct. That left one option. The assumptions underneath the question were wrong. Einstein realized that the whole idea of catching up to light rested on Newtonian assumptions about space and time. The assumption that time flowed at the same rate for everyone. The assumption that distances were absolute. The assumption that if you were moving fast enough, you could make light appear slower or even stationary relative to you. What if those assumptions were the problem? Einstein started with two simple postulates. Two statements that he decided to treat as fundamental, non-negotiable facts about the universe. The first postulate was the principle of relativity. It wasn't new. Galileo had figured this one out centuries earlier, and Newton had built it into his system. The laws of physics are the same in all inertial reference frames. An inertial frame just means you're not accelerating. You're either at rest or moving at constant velocity in a straight line. If you're in that state, the laws of physics apply the same way they do for anyone else in that state. Stand in a room, drop a ball, it falls. Sit in a train moving smoothly at 100 kilometers per hour. Drop a ball. It falls exactly the same way. You can't do an experiment inside the train that tells you you're moving. Not a mechanical experiment anyway. Einstein's genius was in the second postulate. This one was new, and it was the one that broke everything. The speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. Read that again. The speed of light is the same for all observers, not approximately the same, not the same if you correct for your motion, exactly the same, always, no matter what. If you're standing still and you measure the speed of a beam of light, you get about 299,792 kilometers per second. If you're on a rocket ship moving at half the speed of light and you measure the speed of that same beam, you get the same number. Exactly the same. Not faster, not slower, the same. This is not intuitive. This is not how anything else in the universe behaves. If someone throws a ball at you at 50 kilometers per hour and you run toward it at 10 kilometers per hour, the ball approaches you at 60 kilometers per hour relative to you. Speeds add. That's common sense. But light doesn't work that way. Light doesn't care how fast you're moving. Its speed is always the same. The universe has a speed limit, and it's built into the fabric of reality so deeply that no matter what you do, no matter how fast you go, you can never catch up to light. You can never make it appear slower. You can never make it stand still. Einstein took those two postulates and worked out the math. What followed was special relativity, and the consequences were so strange that even he had trouble believing them at first. The first consequence is time dilation. Time does not flow at the same rate for everyone. If you are moving relative to me, I will observe your clock ticking more slowly than mine. Not because your clock is broken, not because of some mechanical quirk, but because time itself is passing more slowly for you from my perspective. This isn't a trick. It's measurable, real, unavoidable. Here's the simplest way to see why it has to happen. Imagine you're on a train and you've built a clock out of light. The clock works like this. A beam of light leaves a bulb on the floor, travels straight up to a mirror on the ceiling, bounces back down, and hits a detector on the floor. Every time the light completes one round trip, that's one tick of the clock. From your perspective, sitting on the train, the light goes straight up and straight down. The distance it travels is just twice the height of the train car. Let's say that height is 3 meters. Light travels at about 300,000 kilometers per second, so the round trip takes a tiny fraction of a second. That's one tick. Now imagine I'm standing on the platform, watching your train go by at high speed. From my perspective, the light doesn't go straight up and down. The train is moving, so while the light is traveling up to the mirror, the train moves forward. The light has to travel diagonally to reach the mirror. Then it travels diagonally back down to hit the detector. The path of the light, from my point of view, is longer than the path you see. But here's the thing. The speed of light is the same for both of us. That's the second postulate. If the light has to travel a longer path from my perspective and the speed is the same, then the time it takes for the light to complete one tick must be longer from my perspective than from yours. Your clock, the light clock on the train, ticks more slowly when I watch it than when you watch it. And since we've built the clock out of light, which moves at the universal speed limit, this isn't just true for this one clock, it's true for time itself. Every process on that train, every chemical reaction, every heartbeat, every thought firing through your neurons, all of it is running slower from my perspective. You don't notice, you can't. From your perspective, you're at rest, your clock ticks normally, your heart beats normally. Time feels the same as it always has. It's only when we compare measurements afterward that the difference shows up. The faster you move relative to me, the more pronounced the effect becomes. At everyday speeds, walking, driving, even flying in a jet, the difference is so tiny it's irrelevant. Your clock might lose a few billionths of a second over the course of a flight. Nobody cares. But as you approach the speed of light, the effect gets dramatic. Move at 90% the speed of light, and from my perspective, your clock ticks at less than half the rate of mine. Move at 99%, and your clock slows to about 1/7. At 99.9%, it's running at less than 1/20th the rate. This isn't science fiction. This has been tested. Physicists have put atomic clocks on airplanes, flown them around the world, and compared them to identical clocks left on the ground. The flying clocks came back younger, not by much, a few hundred nanoseconds. But the difference matched Einstein's prediction exactly. Particles called muons, created when cosmic rays hit the upper atmosphere, decay in about 2 microseconds when measured at rest. But muons traveling at near light speed live much longer from our perspective, long enough to reach the ground before they decay. Their internal clocks are running slow relative to ours. Time dilation keeps them alive. The second consequence is length contraction. If time can stretch, space has to compress. From your perspective on that train, you're at rest and I'm the one moving. And from your perspective, I look compressed, squished along the direction of motion, not in some optical illusion kind of way, actually shorter. This happens because space and time are connected. If your clock is ticking slower from my perspective, then for the universe to stay consistent, the distances you measure have to be different from the distances I measure. Imagine you're moving past me at near light speed. You measure the length of your train car and get, let's say, 10 meters. I measure the same train car as it flies past me, and I get something shorter. At 90% the speed of light, I measure it at about 4.5 meters. You haven't compressed the train. The train hasn't physically crumpled like an accordion. It's just that the distance itself, the space between the front and back of the car, is genuinely shorter in my reference frame than in yours. Again, you don't notice. From your perspective, the train is 10 meters long. Everything inside it behaves normally. It's only from the outside, from someone watching you fly by, that the contraction appears. And just like time dilation, this effect is real. It's been measured. Particle accelerators routinely slam particles together at speeds so close to light speed that the particles are contracted to a tiny fraction of their rest length. The physics of those collisions depends on length contraction being real. And the collisions happen exactly the way Einstein's equations predict. The third consequence, the one that ties everything together, is that nothing with mass can reach the speed of light. Not because we haven't built a fast enough engine, not because we're limited by technology, because the universe won't allow it. As you accelerate closer and closer to the speed of light, something strange happens. It gets harder to accelerate. You push the same amount of force, and you get less and less acceleration in return. The closer you get to light speed, the more energy it takes to go even a tiny bit faster. And as you approach the speed of light itself, the energy required goes to infinity. You can't supply infinite energy. Nobody can. So you can't reach the speed of light. This isn't arbitrary. It's built into the structure of space-time. The speed of light isn't just a speed limit for light. It's the speed limit for causality itself, for cause and effect, for information, for anything that can carry a signal from one place to another. If you could go faster than light, you could send a signal into your own past. You could create a situation where an effect happens before its cause. The universe doesn't allow that. Not because of some cosmic rule written on a stone tablet somewhere, but because faster than light travel is mathematically equivalent to time travel, and time travel of that kind breaks causality in ways that make the universe incoherent. The speed of light, 299,792 kilometers per second, is the speed at which time stops, length shrinks to zero, and mass becomes infinite. It's the boundary between things that can happen and things that can't. It's the edge of the possible. Light itself travels at that speed because light has no mass. Photons, the particles of light, are born moving at light speed and can never slow down. They don't experience time. From a photon's perspective, if you could even call it that, the moment it's emitted from a star and the moment it slams into your retina happens simultaneously. No time passes for the photon itself. It exists in a single eternal instant. For everything else, everything with mass, the speed of light is forever out of reach. You can get close. You can get so close that the difference is measured in decimal places, stretching out for pages. But you can never touch it. The universe has drawn a line, and that line is unbreakable. The Michelson-Morley experiment, the one that failed to find the ether, suddenly made perfect sense. There was no ether. There never had been. Light didn't need a medium to travel through because light wasn't traveling through anything. It was traveling through space-time itself, and space-time didn't drag or compress or flow. It just was. The speed of light was constant because the speed of light was a property of the geometry of the universe. Einstein's paper, published in June of 1905 in a journal called Annalen de Physique, was titled On the Electrodynamics of Moving Bodies. It was 26 pages long. It contained no references, no citations, no footnotes acknowledging earlier work. Just the argument, laid out step by step, built from those two postulates and a lot of very careful algebra. The paper didn't use the word relativity. That term came later, and Einstein didn't set out to overturn Newton. He set out to make sense of light. But what he ended up doing was far bigger. He showed that space and time were not separate. They were not independent. They were woven together into a single structure, a four-dimensional fabric where the separation between events in space and the separation between events in time were two aspects of the same thing, where your measurements of distance and duration depended on how you were moving, where the universe had a built-in speed limit that nothing, not matter, not energy, not information, could ever cross. Newton's absolute space and absolute time were gone. The fixed stage and the universal clock had been replaced by something far stranger. A flexible dynamic geometry where moving clocks ticked slow and moving rulers shrank, and the only thing that stayed constant was the speed of light. Special relativity didn't just tweak Newton's model, it dismantled it, and it did so without requiring any new experimental data. The Michelson-Morley result had been sitting there for 18 years. The constancy of the speed of light had been implied by Maxwell's equations for decades. The pieces were all there. Einstein was the one who put them together and realized that if you took them seriously, if you really believed that the speed of light was the same for everyone, then space and time had to bend. The reaction from the physics community was mixed. Some people got it immediately. Max Planck, one of the most respected physicists in Germany, read the paper and recognized it as a major breakthrough. He corresponded with Einstein, helped promote the work, brought it to the attention of other leading scientists. Others were skeptical, some dismissed it. A few were outright hostile. The idea that time could slow down, that lengths could contract, that simultaneity was relative, all of it felt too strange, too disconnected from everyday experience, and Einstein was nobody. A patent clerk with a PhD nobody had heard of, publishing in a decent but not prestigious journal, making claims that contradicted 200 years of physics. But the math worked. That was the thing. You could argue with the philosophy. You could say it felt wrong. But you couldn't argue with the predictions. They matched the data. They explained things that the old model couldn't. And over the next few years, as more experiments were done, as more tests were run, the evidence piled up. Time dilation was real. Length contraction was real. The constancy of the speed of light was real. special relativity wasn't a curiosity, it was the correct description of how the universe worked. Einstein's revolution was complete. Space and time were no longer the stage and the clock, they were part of the show. Flexible, dynamic, observer-dependent, and at the heart of it all was that one unbreakable rule. The speed of light is the same for everyone, always. That rule forced everything else to bend. Time, space, mass, energy, all of it had to adjust to keep the speed of light constant. And in adjusting, the universe revealed itself to be far stranger, far more interconnected, and far more beautiful than anyone had imagined. But Einstein wasn't done. Special relativity worked perfectly for objects moving at constant speed. But the universe is full of things that accelerate, things that speed up, slow down, change direction, things that fall. And falling, Einstein realized, was the key to something even deeper. Gravity wasn't a force pulling objects together. Gravity was the shape of space-time itself, and that shape could bend, curve, and ripple in ways that made Newton's clockwork universe look like a child's toy. Einstein wasn't satisfied. Special relativity had solved the problem of light, unified space and time, and shown that the universe had a speed limit built into its fabric. But it came with a glaring limitation. It only worked for observers moving at constant velocity. The moment you started accelerating, speeding up or slowing down or changing direction, the equations got messy. More importantly, they didn't say anything useful about gravity, and gravity was everywhere. Newton's law of universal gravitation still worked perfectly for predicting planetary orbits, calculating tides, and explaining why apples fell. But Newton's gravity was a force that acted instantly across any distance. The sun pulled on the Earth, and the Earth pulled back, and that pull happened immediately. No delay, no signal traveling from one body to the other, just instantaneous action at a distance. That bothered Einstein. Special relativity had just shown that nothing, not matter, not energy, not information, could travel faster than light. If the sun suddenly vanished, Earth wouldn't feel the change in gravity for about 8 minutes, the time it takes light to travel from the sun to Earth. There had to be a speed limit for gravity too. Newton's instantaneous force couldn't be the full story, so Einstein set out to fix it. What he ended up doing was far more radical than fixing. He replaced gravity entirely. What emerged was general relativity, published in 1915 after 8 years of the hardest intellectual work of his life. And at the heart of it was an idea so simple, so elegant, and so strange that it's still hard to fully believe, even though we've tested it thousands of times. Gravity isn't a force. Gravity is geometry. Mass doesn't pull on other mass. Mass bends space and time, and that bending is what we experience as gravity. The breakthrough came from an insight Einstein had in 1907, sitting in his office at the Patent Bureau in Bern. He called it the happiest thought of his life. He imagined a man falling off a roof. While the man was falling, before he hit the ground, he wouldn't feel his own weight. If he pulled a coin out of his pocket and let it go, the coin wouldn't fall relative to him. It would just float there next to him, both of them plummeting toward the ground together. For that brief moment of free fall, the man would feel weightless, exactly as weightless as an astronaut floating in orbit, exactly as weightless as someone drifting in deep space, far from any planet or star. There would be no experiment the falling man could do, no measurement he could make that would tell him he was in a gravitational field. From his perspective, gravity would have vanished. Einstein realized this wasn't a coincidence, it was a clue. Gravity and acceleration were two sides of the same coin. If you were standing on the surface of the Earth, you felt weight because the ground was accelerating you upward. The ground was pushing on your feet, preventing you from following the natural path you'd take if nothing was in the way. That natural path was freefall. And in freefall, gravity disappeared. This became the equivalence principle. Locally, in a small enough region of space and time, the effects of gravity are indistinguishable from the effects of acceleration. If you woke up in a windowless room and felt yourself being pushed into the floor, you couldn't tell whether you were standing on the surface of a planet or sitting in a rocket accelerating through space at 9.8 meters per second squared. The physics would be identical. This idea sounds abstract, but it's testable. Take two objects of different masses, say a hammer and a feather, drop them in a vacuum where air resistance doesn't interfere. They fall at the same rate. Galileo supposedly demonstrated this at the Pisa Tower, though the story is probably apocryphal. Apollo 15 astronaut David Scott actually did it on the moon in 1971, dropping a hammer and a feather side by side. They hit the lunar surface at the same time. In Newtonian physics, this is a coincidence. The hammer has more mass, so gravity pulls on it harder. But the hammer also has more inertia, so it's harder to accelerate. The two effects exactly cancel, and everything falls at the same rate. Newton noticed this, measured it carefully, but never really explained why it had to be true. Einstein's equivalence principle made it inevitable. If gravity and acceleration are the same thing, then of course everything falls at the same rate. Because in an accelerating rocket, a hammer and a feather also accelerate at the same rate. They have to. They're not being pulled by a force. They're just moving through spacetime, and spacetime itself is structured in a way that makes all objects follow the same paths. That structure is curvature. Einstein spent years working out the mathematics, learning differential geometry, a branch of math that describes how surfaces and higher dimensional spaces can bend and twist. He needed help. He collaborated with his friend Marcel Grossmann, a mathematician who knew the tools Einstein needed but had never thought to apply them to physics. The idea, in its simplest form, goes like this. Space-time isn't just a stage where things happen. It's a fabric, a four-dimensional structure where three dimensions are space and one is time, all woven together. Mass and energy curve this fabric. The more mass, the more curvature, and objects moving through space-time follow the straightest possible paths through that curved geometry. A planet orbiting a star isn't being pulled by a force. It's moving in a straight line through curved space-time. The curvature is what makes the path look like an ellipse from the outside. The planet is just doing what any object does when left alone, following the geometry. This is hard to visualize because we're not built to see four-dimensional curvature. The usual analogy is a rubber sheet. Imagine stretching a flat rubber sheet tight, then placing a heavy ball in the middle. The sheet sags around the ball. Now roll a marble across the sheet. The marble's path will curve as it moves through the dip created by the heavy ball. If you roll it at just the right speed and angle, it might even orbit the ball, circling around the depression without falling in. That's a rough picture of how general relativity works. The heavy ball is the sun. The marble is a planet. The dip in the rubber sheet is the curvature of space-time. The planet isn't being pulled, it's rolling along the curved surface. The analogy breaks down in a lot of ways. Real space-time curvature happens in 4 dimensions, not 2. And the curvature affects time as much as it affects space. But the rubber sheet gives you the intuition. Gravity isn't a force reaching across space to pull things together. Gravity is what happens when you try to move through a region of space-time that isn't flat. John Archibald Wheeler, one of the great physicists of the 20th century and a master of vivid language, summarized general relativity in a single sentence. Matter tells space-time how to curve, and space-time tells matter how to move. That's it. That's the entire theory. Everything else is working out the details. The equation Einstein wrote down to describe this relationship is called the Einstein field equation. It's deceptively short, just a few symbols when written in the compact notation physicists use. But those symbols represent a set of 10 interrelated equations, each one a differential equation connecting the curvature of spacetime at every point to the distribution of mass and energy at that point. Solving those equations for anything but the simplest cases is brutally hard. Einstein himself only managed to find exact solutions for a few special scenarios. Other physicists spent decades finding solutions for black holes, expanding universes, rotating masses, and gravitational waves. Some of those solutions predicted things so strange that even Einstein didn't believe them at first. But before any of that, Einstein needed to show that his theory worked, that it made predictions different from Newton's gravity, that those predictions could be tested, and that when you tested them, general relativity came out on top. The first test was sitting right there in the data, waiting. Mercury's orbit had been a thorn in the side of Newtonian gravity for decades. Mercury, the closest planet to the Sun, traces out an ellipse as it orbits. But the ellipse itself rotates slowly over time. The point where Mercury comes closest to the Sun, called the perihelion, shifts a tiny bit with each orbit. Over a century, the perihelion advances by about 5,600 arcseconds. That's about 1.5 degrees, a tiny shift. Most of that shift could be explained by the gravitational pull of the other planets tugging on Mercury as they orbited. Jupiter, Venus, Earth, all of them exerted small forces that perturbed Mercury's orbit in predictable ways. Astronomers could calculate those perturbations using Newton's laws and subtract them out. After subtracting everything they could account for, there was a leftover. 43 arcseconds per century, a tiny, stubborn residual that refused to go away. Some astronomers even proposed the existence of a new planet closer to the Sun than Mercury that could account for the extra precession. They called it Vulcan. They looked for it. They never found it because it didn't exist. Einstein calculated what general relativity predicted for Mercury's orbit. In curved spacetime, especially in the strong gravitational field close to the Sun, the orbit should precess slightly more than Newton's gravity predicted. He worked through the math, plugged in the numbers for Mercury's mass, the Sun's mass, the distance between them. The answer came out to 43 arcseconds per century. Exact match, no fudging, no adjustable parameters. Just the theory, applied honestly, predicting the precise value that had been measured but never explained. Einstein later said that when he saw this result, he had heart palpitations. For days afterward, he was so excited he could barely work. This wasn't just a successful prediction. It was proof that general relativity reached into the deepest workings of the solar system and got the details right in a way Newton's gravity couldn't. The second test was more dramatic. General relativity predicted that light, which has no mass, should still be affected by gravity, not because gravity pulls on light, but because light travels through spacetime, and spacetime can be curved. A beam of light passing near a massive object should follow the curvature, bending its path. Newton's gravity also predicted a tiny bit of light bending, treating light as if it were made of particles with mass. But general relativity predicted twice as much bending, twice, a clear difference, testable. The best way to test it was during a total solar eclipse. Normally, you can't see stars near the Sun because the Sun's light drowns them out. But during an eclipse, the Moon blocks the Sun's light, and suddenly stars near the Sun's edge become visible. If you photographed those stars and compared their positions to where they appeared at night when the Sun was nowhere near them, you could measure how much their light had bent as it passed close to the Sun. In 1919, 2 British expeditions set out to do exactly that. One team, led by Arthur Eddington, traveled to the island of Principe off the coast of West Africa. The other went to Sobral in Brazil. Both locations were in the path of a total solar eclipse on May 29th. The war had just ended. Einstein was German. The expeditions were British. The fact that British scientists were testing the theory of a German physicist so soon after World War I was itself remarkable. The observations weren't easy. Clouds interfered. The equipment was finicky. The measurements required extraordinary precision. But when the data was analyzed, the result was clear. Starlight bent by the sun, and the amount of bending matched Einstein's prediction, not Newton's. The announcement made headlines around the world. The Times of London ran the story under the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Overnight, Einstein became the most famous scientist on the planet, not just among physicists, among everyone. His picture was in newspapers. Strangers recognized him on the street. He was invited to give lectures, attend dinners, meet world leaders. General relativity wasn't just correct, it was glamorous, exotic, a glimpse into a reality stranger and more beautiful than anything people had imagined. Space itself could bend, time itself could stretch, and the universe, it turned out, was far weirder than the clockwork machine Newton had described. One of the strangest predictions of general relativity is gravitational time dilation. In special relativity, time slows down when you move fast. In general relativity, time slows down when you're deep in a gravitational field. Clocks on the surface of the Earth tick slightly more slowly than clocks high above the Earth. The closer you are to a massive object, the slower time passes for you relative to someone farther away. This isn't a malfunction of the clock. It's not a measurement error. Time itself runs slower. If you spent a year standing at sea level and I spent a year on top of a mountain, when we met up again, I would be older than you by a few billionths of a second. Not much, but measurable. The effect gets more dramatic near stronger gravitational fields. On the surface of a neutron star, where gravity is millions of times stronger than on Earth, time runs noticeably slower than it does in empty space. Near the event horizon of a black hole, time slows to a crawl. If you watched someone fall toward a black hole, you'd see them slow down, moving more and more sluggishly as they approached the horizon, their clock ticking slower and slower until they appeared to freeze at the edge, their light redshifting into darkness. From their perspective, they'd fall straight through in a finite amount of time. From yours, they'd never quite reach the horizon. Both perspectives are correct. Time itself is relative, bent by the gravity of the black hole. This isn't abstract, we see it. Gravitational time dilation has been measured in experiments so precise that they can detect the difference in time passing between two clocks separated by just a few centimeters of height. Atomic clocks are sensitive enough to register the tiny change in gravitational field strength over distances you could reach by climbing a short ladder. And we rely on it every day. Because the Global Positioning System, GPS, depends on satellites orbiting about 20,000 kilometers above Earth's surface. Those satellites experience weaker gravity than clocks on the ground, so their clocks tick faster, about 45 microseconds faster per day. At the same time, the satellites are moving at high speed relative to the ground, so special relativity makes their clocks tick slower by about 7 microseconds per day. The net effect is that satellite clocks run about 38 microseconds faster per day than ground clocks. That doesn't sound like much, but GPS works by measuring the time it takes radio signals to travel from satellites to receivers on the ground. Light travels about 30 centimeters in 1 nanosecond. 38 microseconds is 38,000 nanoseconds. If you didn't correct for general and special relativity, your GPS position would drift by about 11 kilometers per day. Your phone's map app works because Einstein was right. Every turn-by-turn direction you've ever followed, every location you've ever pinned, every rideshare pickup you've ever coordinated, all of it depends on satellites whose clocks have been adjusted to account for the curvature of space-time. There's more evidence. Gravitational lensing, the bending of light by massive objects, has been observed thousands of times. Galaxy clusters bend the light from galaxies behind them, creating multiple distorted images, arcs, and rings of light stretched across the sky. Astronomers use this effect to map the distribution of dark matter, which doesn't emit light but does curve space-time. In some cases, a foreground galaxy perfectly aligns with a background galaxy, and the light bends into a complete circle around the foreground object. It's called an Einstein ring, a direct, visible manifestation of space-time curvature. Gravitational waves, ripples in space-time itself, caused by accelerating masses, were predicted by general relativity in 1916. Einstein thought they'd be too weak to ever detect. He was almost right. It took 100 years and the most sensitive instruments ever built, but in 2015, the LIGO Observatory detected gravitational waves from two black holes colliding more than 1 billion light-years away. The signal was a chirp, a rising tone lasting a fraction of a second as the black holes spiraled together and merged. The detection was so precise that scientists could measure the stretching and squeezing of space itself by distances smaller than the width of a proton. Since then, dozens of gravitational wave events have been detected: colliding black holes, merging neutron stars, each one a confirmation that space-time is real, dynamic, and capable of carrying information across the universe in the form of ripples in its own fabric. General relativity also predicted black holes, though Einstein didn't like the idea. The equation showed that if you compressed enough mass into a small enough region, the curvature of space-time would become so extreme that nothing, not even light, could escape. A point of no return, the event horizon. Beyond that boundary, space-time itself curves so sharply inward that every possible future path leads toward the center. You can't turn around, you can't stop, you can't even stay still. The geometry won't let you. Black holes exist. We've found them. Stellar mass black holes scattered throughout the galaxy. Supermassive black holes at the centers of galaxies, some weighing billions of times the mass of the Sun. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow, a dark circle surrounded by glowing gas, sitting in the center of a galaxy 55 million light-years away. The shape, the size, the glow, all of it matched what general relativity predicted. Einstein gave us a universe where space and time are woven together, where gravity is geometry, where massive objects don't pull, they curve, where time doesn't flow the same for everyone, where the paths objects follow through the cosmos are determined not by forces acting at a distance, but by the shape of the fabric they're moving through. And that fabric is everywhere. You're not standing on solid ground right now because the earth is pulling you down. You're standing here because the ground is in your way. The Earth's mass curves space-time, and your natural path through that curved geometry is to accelerate toward the center. The ground blocks that path. It pushes up on you. That push is what you feel as weight. If the ground vanished, you'd fall. But from your perspective, in free fall, gravity would disappear. You'd float, weightless, free, following the straightest possible path through curved space-time. Not because a force stopped acting on you, because you'd finally be allowed to move the way space-time wants you to move. This is what general relativity revealed. The universe isn't a container. It's not a stage with objects moving across it. The universe is the objects, the space between them, the time connecting events, all of it woven into a single dynamic structure, a structure that bends, flexes, ripples, and guides everything within it. Newton gave us a universe that ran like a machine, predictable, deterministic, separate from the observer. Einstein gave us a universe that is participatory. Your motion affects space-time. Space-time affects your motion. Clocks disagree. Distances change. And nothing, not space, not time, not gravity, is absolute anymore. The patent clerk had done it again. But this time, the revolution was even deeper. Special relativity had united space and time. General relativity had shown that this union wasn't passive. Space-time was alive, responsive, shaped by matter and energy, shaping matter and energy in return. And every clock, every orbit, every beam of light bending around a distant galaxy, every satellite helping you find your way home, was proof that Einstein had seen something true. You've probably used GPS today without thinking twice about it. Your phone knows where you are. It can guide you to a restaurant, track your run, or find the nearest coffee shop that isn't a Starbucks. The precision is so routine that you complain when it's off by 20 meters, as if the universe owes you better. But that precision, the fact that a device in your pocket can pinpoint your location to within a few meters anywhere on Earth, is only possible because Einstein was right. Not abstractly right, not philosophically right. Right in a way that shows up in the engineering, in the code, in the corrections that run every single second on every single GPS satellite orbiting above your head right now. If general and special relativity weren't real, if time didn't actually dilate with speed and gravity, your GPS would be off by kilometers within hours. It would drift so fast, it'd be useless for navigation by the end of the day. The fact that it works, that it keeps working, that you can trust it to tell you where you are while you're driving 70 kilometers per hour down a highway you've never been on before, is one of the most concrete pieces of evidence we have that space-time isn't just an elegant theory. It's the structure of reality. Let's talk about how GPS actually works, because the details matter. The system relies on a constellation of satellites, currently about 30 of them, orbiting Earth at an altitude of roughly 20,000 kilometers. That's high. For context, the International Space Station orbits at about 400 kilometers. These GPS satellites are 50 times higher, moving at about 14,000 kilometers per hour, circling the planet twice a day. Each satellite carries an atomic clock, not a regular clock, not even a good clock. An atomic clock, one of the most precise timekeeping devices humans have ever built. These clocks are accurate to within a few billionths of a second per day. They tick based on the vibrations of atoms, specifically cesium or rubidium atoms, oscillating at frequencies so stable that they make quartz watches look like sundials. The satellites don't do much. They broadcast a signal. That's it. The signal contains two pieces of information: the exact time the signal was sent, as measured by the satellite's atomic clock, and the satellite's position in space at that moment. That's all. Time and location, broadcast continuously, over and over. Your phone or your car's GPS receiver listens. It picks up signals from multiple satellites simultaneously, usually at least 4, sometimes more. For each satellite, the receiver does a simple calculation. It compares the time the signal was sent to the time the signal arrived. The difference tells you how long the signal was in transit. Multiply that time by the speed of light, about 300,000 kilometers per second, and you get the distance from your receiver to that satellite. Do that for 4 satellites, and you've got 4 distances. Each distance defines a sphere. You're somewhere on the surface of a sphere centered on satellite 1, somewhere on the surface of another sphere centered on satellite 2, and so on. The point where all four spheres intersect is your location, 3 dimensions of space plus 1 extra measurement to correct for timing errors in your receiver's cheap quartz clock. The math is straightforward, the precision is not. Light travels about 30 centimeters in 1 nanosecond, 1 billionth of a second. If your timing is off by just 10 nanoseconds, your calculated position is off by 3 meters, 100 nanoseconds, 30 meters, a microsecond, 300 meters. GPS needs to be accurate to within a few meters. That means the timing has to be accurate to within tens of nanoseconds, not approximately accurate, exactly accurate. And that's where relativity shows up, uninvited and unavoidable. The satellites are moving fast, 14,000 kilometers per hour relative to the surface of the Earth. That's about 4 kilometers per second, not anywhere close to the speed of light, which is 300,000 kilometers per second, but fast enough that special relativity starts to matter. According to special relativity, moving clocks tick slower than stationary clocks. From the perspective of someone standing on Earth, the atomic clocks on those satellites should be running slow, not by much, but by a measurable amount. The formula for time dilation in special relativity depends on speed. Specifically, it depends on the square of your speed divided by the square of the speed of light. For GPS satellites moving at about 4 kilometers per second, you can plug in the numbers. The calculation shows that the satellite clocks lose about 7 microseconds per day compared to clocks on the ground. 7 microseconds, 7 millionths of a second. That doesn't sound like much. It's not much in absolute terms. But remember, light travels 300 meters in 1 microsecond. 7 microseconds is 2 kilometers. If you didn't account for this effect, your GPS position would drift by about 2 kilometers per day just from special relativity alone. That's bad, but it's not the whole story. Because the satellites aren't just moving, they're also higher up in Earth's gravitational field, much higher. And general relativity says that clocks in weaker gravitational fields tick faster than clocks in stronger fields. On the surface of the Earth, you're deep in the planet's gravitational well. Spacetime is curved by Earth's mass, and that curvature makes time pass slightly slower for you than it does for someone farther away. The GPS satellites, orbiting at 20,000 kilometers, are much farther out. The gravitational field they experience is weaker. Spacetime is less curved, and their clocks, as a result, tick faster. The calculation for gravitational time dilation is more complicated, but the effect is larger. The satellite clocks gain about 45 microseconds per day compared to clocks on the ground. 45 microseconds. That's 13.5 kilometers of position error per day if left uncorrected. Now you've got 2 effects pulling in opposite directions. Special relativity makes the satellite clocks run slow by 7 microseconds per day. General relativity makes them run fast by 45 microseconds per day. The net effect is that the satellite clocks run fast by about 38 microseconds per day. 38 microseconds per day translates to roughly 10 to 11 kilometers of error per day in your calculated position. Within a week, your GPS would be off by over 70 kilometers. Within a month, hundreds of kilometers. The system would be useless. This isn't hypothetical. It's not a thought experiment. When GPS was being designed in the 1970s, engineers had to account for relativity. Some of them didn't want to. The corrections felt like overkill, an unnecessary complication in an already complex system. There were debates. Some engineers argued that the effects were too small to matter. Others pointed out that atomic clocks were precise enough to detect the difference, and if the clocks could detect it, the system would drift. The decision was made to build the corrections in from the start. The atomic clocks on the satellites are deliberately set to tick at a slightly different rate than clocks on the ground. Before launch, they're adjusted to run slow by about 38 microseconds per day. Once they're in orbit, moving fast, and sitting in a weaker gravitational field, the relativistic effects kick in, and the clocks end up ticking at the same rate as ground clocks. Problem solved. This isn't a one-time adjustment. The system continuously monitors the satellite clocks, comparing them to a network of ground-based atomic clocks maintained by the United States Naval Observatory and other timing facilities around the world. The corrections are updated in real time, compensating for tiny variations in the satellite's orbits, speed, and altitude. The relativistic adjustments are part of the standard operating procedure. They're not optional, they're required for the system to function, and it does function brilliantly. GPS is so reliable, so accurate, that entire industries depend on it. Shipping, aviation, agriculture, telecommunications, power grids, financial transactions that require precise timestamps. All of it relies on satellites whose clocks are adjusted for relativity. Your phone's map app isn't just a convenience. It's a piece of technology that works because space-time is curved, because time dilates with speed and gravity, because Einstein's equations, written down more than a century ago, describe the universe accurately enough that engineers can use them to synchronize clocks orbiting 20,000 kilometers above the planet. That's the everyday proof. GPS is relativity in action, not a test, not an experiment. A tool, something you use without thinking. And every time it works, every time it tells you where you are, it's confirming that space and time are not separate, not absolute, not fixed. They're flexible, dynamic, observer-dependent, and they behave exactly the way Einstein said they would. GPS isn't the only place relativity shows up in the real world. Particle accelerators provide another direct, undeniable demonstration. These are the massive machines physicists use to smash particles together at near-light speeds to study what they're made of. The Large Hadron Collider, the most powerful accelerator ever built, sits in a circular tunnel 27 kilometers around, buried beneath the border between France and Switzerland. Inside that tunnel, protons are accelerated to 99.999% the speed of light. At that speed, special relativity predicts that time should run much slower for the protons than for the scientists watching them. And it does, measurably, unmistakably. Protons are stable particles, they don't decay. But some of the particles created in collisions inside the accelerator are unstable. Take muons, for example. Muons are heavier cousins of electrons. When they're at rest, they decay in about 2 microseconds on average, 2/millionths of a second. That's their half-life. Wait 2 microseconds and half of your muons will have decayed into other particles. But when muons are moving at near light speed, they last much longer, not because they're more stable, not because the decay process slows down in some chemical or nuclear sense, because time itself is passing more slowly for the muons relative to the lab. From the lab's perspective, the muons live for tens of microseconds, sometimes hundreds, before decaying. From the muon's perspective, if you could ask one, only 2 microseconds pass. The muon doesn't experience a longer life. It experiences exactly the amount of time it always does. But the distances it travels appear shorter to the muon because of length contraction. Same trip, different measurements of time and space, depending on who's doing the measuring. The particles don't know about relativity. They don't need to. They're just moving through space-time, and space-time bends the measurements in exactly the way Einstein predicted. The physicists running the accelerators don't treat this as a curiosity. They treat it as a fact of life. The equations they use to predict particle trajectories, collision energies, and decay rates all include relativistic corrections. Without those corrections, the predictions would be wrong. The experiments wouldn't work. Atomic clocks provide yet another confirmation. These clocks are so sensitive that they can detect gravitational time dilation over distances you can measure with a tape measure. In 2010, physicists at the National Institute of Standards and Technology in Colorado ran an experiment where they compared two atomic clocks separated by just 33 centimeters in height, 1/3 of a meter, a little over a foot. The clock that was higher, farther from Earth's center, farther out of the gravitational well by a trivial amount, ticked faster. The difference was tiny, about 90 parts in a quintillion, but it was there, detectable, real. Gravity at your feet is slightly stronger than gravity at your head. Time at your feet passes slightly slower. The effect is so small that over the course of your entire life, your head ages about 90 nanoseconds more than your feet. You will never notice, but it's happening. Physicists have also flown atomic clocks on airplanes and compared them to clocks left on the ground. This was done in the early 1970s, not long after atomic clocks became accurate enough to detect the effect. The flying clocks, moving faster than the ground clocks, ticked slower due to special relativity. But they were also higher up, farther from Earth's mass, so they ticked faster due to general relativity. When the planes landed and the clocks were compared, the measured differences matched Einstein's predictions, both effects, both exactly right. The GPS satellites orbiting overhead right now are running the same experiment continuously. The difference is that GPS doesn't just measure the effect, it depends on it. The system wouldn't function without the corrections. And because billions of people use GPS every day, because it works reliably, because your phone can tell you that you're standing on the corner of 5th Avenue and 23rd Street and be correct to within a few meters, you have evidence in your pocket that relativity is real. This is worth pausing on. A lot of modern physics feels distant, abstract. Quarks, dark matter, the expansion of the universe, those things don't show up in your daily life. You can live your entire life without ever encountering a situation where quantum mechanics or cosmology affects anything you care about. Relativity is different. You use it every day, every time you check your location, every time you navigate to an address you've never been to, every time a delivery truck finds your house, or a plane lands on a runway, or a ship docks at a port. All of that precision, all of that coordination relies on satellites whose clocks are adjusted for the curvature of spacetime. The engineers who built GPS didn't sit around philosophizing about the nature of time. They sat around trying to make a navigation system that worked. And when they did the math, when they tested the prototypes, when they compared predictions to measurements, relativity kept showing up, not as a theory, as a correction factor, a necessary adjustment, a piece of reality that couldn't be ignored. Einstein never saw GPS. He died in 1955, decades before the first GPS satellite launched. But he saw this coming, not GPS specifically. He couldn't have predicted the technology, but he understood that if his theories were correct, they would show up in practical applications, that clocks would disagree, that distances would change, that time and space would behave in ways that violated common sense but matched the math. And he was right, not approximately, not metaphorically, precisely, quantitatively, right in a way that you can measure with instruments and verify with experiments and use to build systems that billions of people depend on. The GPS paradox, if you want to call it that, is that the system proves relativity works, while most people using it have no idea relativity is involved. You pull up a map on your phone. The map shows a blue dot. That's you. The dot is accurate because a network of satellites 20,000 kilometers above your head are comparing the timing of radio signals with a precision measured in nanoseconds, and the timing has been corrected for the fact that time runs faster in orbit than on the ground. None of that is visible. None of it feels strange when you use it. The interface is simple. The experience is seamless. The weirdness is hidden in the engineering, buried in correction factors and clock adjustments and orbital calculations. But it's there, running, right now, and the implications go deeper than navigation. If time can run at different rates, depending on how fast you're moving and how deep you are in a gravitational field, then time isn't a universal background ticking away the same for everyone. It's local, personal. Your time is not my time. We can synchronize our clocks, sure, but only if we agree on a reference frame. Only if we're moving the same way through the same gravitational field. The moment we separate, the moment you get on a plane and I stay on the ground, or you climb a mountain and I stay at sea level, our clocks start to diverge, slowly, imperceptibly in everyday life, but measurably, actually, for real. GPS makes this tangible. You don't have to imagine astronauts aging slower, or twins on rockets, or any of the usual thought experiments. You just have to look at the satellites. They're up there, moving fast, experiencing weaker gravity. Their clocks are ticking faster than yours, not in theory, in practice, in a way that engineers have to correct for, or the system breaks. This is the bridge between Einstein's abstract ideas and the world you live in. Special relativity says moving clocks run slow. General relativity says clocks in weak gravity run fast. GPS says both of those effects are real, measurable, and significant enough that ignoring them would cripple a technology used by billions. And if time can bend, if it can stretch and compress depending on motion and gravity, then time isn't the steady universal flow Newton described. It's not the cosmic metronome ticking in the background of reality. It's part of the fabric, woven into space, responding to mass and energy, flexible, which raises a question that GPS can't answer but forces you to ask. If your time and my time can run at different rates, if the past and future aren't the same for everyone, if now depends on where you are and how you're moving, then what is time really? What does it mean for something to happen now when now is different for every observer? That question doesn't have an easy answer. It might not have a comfortable answer, but it's the question that leads to the next step, to the idea that time, as we experience it, flowing from past to future, moment by moment, might not be the whole story. That the universe might contain every moment that has ever happened and ever will happen, all at once, woven into a single four-dimensional structure where past, present, and future are just directions, places you can point to on a map. GPS proves that space-time is real, that time isn't absolute, that the universe doesn't care about your intuition or your experience. It follows the math. And the math, when you take it seriously, when you follow it all the way through, leads somewhere strange. You've just finished wrapping your head around GPS, around the fact that satellites orbiting overhead need their clocks adjusted for relativity, or your map app stops working. You've accepted, maybe reluctantly, that time isn't absolute, that your clock and my clock can tick at different rates depending on how we're moving and where we're standing in a gravitational field. That's already strange, but it's concrete, measurable. Engineers deal with it. The corrections show up in code, in hardware, in systems that millions of people use every day without thinking about the physics underneath. But there's a consequence buried in all of this that's far stranger. One that most people never encounter because it doesn't affect GPS or particle accelerators or anything you can build. It's philosophical, conceptual. The kind of idea that makes you stop and stare at the wall for a while, because if it's true, and the math says it might be, then everything you think you know about time, about the present moment, about the difference between past and future, is wrong. The idea is called the block universe. Sometimes it's called eternalism, and it says this: every moment that has ever happened, every moment that is happening right now, and every moment that will ever happen in the future, all of them exist, not existed, not will exist right now, simultaneously, all at once, laid out in a four-dimensional structure where past, present, and future are just directions you can point, like north and south. Your birth exists, your death exists. The moment you're experiencing right now, reading these words, or hearing this voice, exists. And so does every other moment of your life, frozen in space-time, like frames in a film strip. You're not moving through time. Time isn't flowing. You, the conscious you reading this, are just aware of one slice of the block at a time. The present moment you feel so vividly, the sense that right now is special, that it's the only moment that's real, is an illusion, a trick of perception. The universe doesn't have a now, it has a space-time, and in that space-time, past and future are just as real as the present. That's the block universe, and if you're feeling uncomfortable, good, you should be, because this idea, if it's correct, upends nearly everything about how humans experience reality. Let's start with why anyone takes this seriously. Because it's not just philosophers sitting around imagining strange possibilities. The block universe is a direct consequence of Einstein's relativity. Specifically, it's a consequence of something called the relativity of simultaneity. Here's the problem. In everyday life, you have a very clear sense of what now means. Right now, you're reading this. Right now, somewhere across the planet, someone is eating breakfast. Someone else is going to sleep. Those events are all happening now, at the same time, simultaneously. But Einstein's relativity says that simultaneity, the idea that two events happen at the same time, is not absolute, it's relative. It depends on your reference frame, on how you're moving. Imagine two people, Alice and Bob, standing on a train platform. A train goes by at high speed. Right as the middle of the train passes between them, two bolts of lightning strike the platform. One hits near Alice, one hits near Bob. The strikes are perfectly synchronized. They happen at exactly the same time, according to Alice and Bob, who are both standing still on the platform. But there's a third person, Carol, sitting in the exact middle of the train. From her perspective, moving with the train, the lightning strikes are not simultaneous. She sees the bolt near the front of the train, the one the train is moving toward, slightly before she sees the bolt near the back. Not because the light takes longer to reach her. The geometry of space-time itself makes the events non-simultaneous in her reference frame. This isn't an optical illusion. It's not about signal delays. When you account for the travel time of light and do the math carefully, the events genuinely happen at different times, according to Carol. For her, one strike happens first. For Alice and Bob, they happen simultaneously. Both perspectives are correct. There is no absolute answer to the question, did these events happen at the same time? The answer depends on who you ask. And if simultaneity is relative, then the present moment is relative. Your now is not the same as someone else's now if they're moving relative to you. And if the present moment is relative, if there's no universal now that everyone agrees on, then what does it mean to say that only the present exists? This is the crack that breaks the intuitive view of time. The view where the past is gone, the future hasn't happened yet, and the present is the only thing that's real. That view requires a universal present, a single moment, right now, that everyone in the universe shares. But relativity says there is no such thing. Different observers have different presents. Events that are in your future might be in someone else's past. And if there's no universal now, then all moments, past, present, and future, have to exist in some sense. Otherwise, what are we even talking about when we say an event happens? The block universe takes this seriously. It says that space-time is a four-dimensional structure, and every event that ever happens occupies a specific location in that structure. Your birth is at one set of coordinates. Your 10th birthday is at another. The moment you're experiencing right now is at another. Your death is at another. All of those coordinates exist in the block. None of them is more real than any other. The present moment you're experiencing is just the slice of the block that your consciousness happens to be aware of right now. Think of it like a movie. A film strip has every frame of the movie already printed on it. The frames don't appear one at a time as you watch. They're all there, laid out along the strip. When you watch the movie, you see one frame, then the next, then the next. The illusion of motion, of time passing, comes from your brain stitching those static frames together. But the frames themselves aren't moving. They're just sitting there on the strip, frozen. The block universe says the universe is like that film strip. Every moment of your life, every moment of history, every moment of the future is a frame already printed on the strip. You, the conscious experiencing you, are like the projector light moving along the strip. You illuminate one frame, experience it, then move to the next. The sense that time is flowing, that the present is moving forward, is just your awareness sliding along the block. The block itself doesn't change, it doesn't move, it just is. This is eternalism, the view that all times are equally real, past, present and future all exist. The universe is a static four-dimensional object, and time is just one of the dimensions, no more special than space. The alternative view, the one that matches common sense and human intuition, is called presentism. Presentism says that only the present exists. The past existed, but it doesn't anymore. The future will exist, but it doesn't yet. Right now, this moment, is the only moment that's real. The past is gone, the future is open, and time genuinely flows from one moment to the next. Presentism feels right. It matches how we experience life. You remember the past, but you can't touch it. You anticipate the future, but it hasn't happened yet. The present is where you live. It's the only place you've ever been. The only place you can ever be. But presentism has a problem. It requires a universal present, a single moment, right now, that defines what exists. And relativity says there is no such moment. Different observers have different presents. If you're on Earth and I'm on a spaceship moving at near light speed, your present moment and my present moment don't align. Events that are in your present might be in my past or my future. So which present is the real one? Whose now gets to define what exists? Presentism doesn't have a good answer. The block universe does. It says there is no universal present because there doesn't need to be. All moments exist. Your present and my present are both real. They're just different slices through the same four-dimensional structure. This isn't a popular idea. Not because physicists have disproven it, because it's deeply uncomfortable. The block universe says that everything that will ever happen to you has already happened in a sense. Your future is already laid out. Every decision you'll ever make, every mistake, every triumph, every moment of joy and pain and confusion, it's all already there in the block, waiting, existing, frozen. That raises the obvious question. If the future already exists, then is it fixed? If your entire life is already printed on the film strip, do you have any choice in how it plays out? Or are you just watching a movie that's already been made, experiencing the illusion of choice while following a script that was written before you were born? This is where the block universe crashes headfirst into free will, and the collision is ugly. Free will, the sense that you could have done otherwise, that your choices are real and meaningful and open, seems to require an open future. A future that doesn't exist yet. a future that you help create through your decisions. If the future is already there, already real, already determined, then what are you choosing? You're not creating the future, you're discovering it. Frame by frame, one moment at a time. Some philosophers argue that the block universe and free will are compatible. They say that even if your entire life exists in the block, your decisions are still real. They're part of the structure. The choices you make at each moment are what determine which frame comes next. The fact that all the frames exist doesn't mean you didn't choose them. It just means the choosing is part of the block. Other philosophers aren't convinced. They point out that if your future self already exists in the block, then the decisions that lead to that future must already be determined. You can't make a different choice because the block is fixed. The future you that exists in the block is the result of the choices you will make, and those choices are already part of the structure. You're not free to choose differently because differently doesn't exist. The block contains one timeline, yours, and you're living it whether you like it or not. This debate has been going on for decades and shows no sign of resolution. The block universe doesn't prove free will doesn't exist. It just makes it harder to define, harder to defend, harder to reconcile with the sense, the very strong sense, that your choices matter. And yet the math keeps pointing toward the block. Relativity doesn't care about your discomfort. It doesn't care that the idea of a fixed future feels wrong. It just keeps insisting that simultaneity is relative, that there's no universal now, and that if you take space-time seriously, you end up with a structure where all events coexist. There's a way to visualize this that might help, or might make it worse. Imagine space-time as a loaf of bread. The loaf is the entire history of the universe, from the Big Bang to the distant future, all baked into one solid object. Each slice of the bread is a moment in time, a snapshot of the entire universe at one instant. Now here's the thing. There's no single correct way to slice the loaf. You can slice it straight across, perpendicular to the long axis. That's one way to define the present moment, but someone moving relative to you would slice the loaf at a different angle. Their slices would be tilted compared to yours. Events that fall into one of your slices might fall into a different slice for them. Your present and their present don't line up. Both of you are cutting through the same loaf. The loaf itself doesn't change, it's the same bread. But the slices are different. The present moment is not a property of the loaf, it's a property of how you're slicing it. And because there's no preferred way to slice the loaf, there's no preferred present moment. All the slices are equally valid, all the moments exist. This is what relativity tells us, and the block universe is what you get when you take that seriously. Now, the block universe isn't the only game in town. There are other models, other ways to think about time that try to preserve some sense of flow, some sense of becoming, without requiring a universal present. One is called the growing block universe. It says that the past and present exist, but the future doesn't. The block is real, but it's not complete. It's growing. Every moment, the present moment becomes part of the past, and a new slice of the block comes into existence. Time genuinely flows in this model. The future is open because it hasn't been added to the block yet. Your choices help determine what gets added. The past is fixed, the present is real. The future is empty. This feels a bit more comfortable than the full block. It gives you an open future. It preserves the sense that time is moving, that something is genuinely happening as one moment becomes the next. But it still has problems. For one thing, it requires a universal present, a single moment where the block stops and the future begins. And relativity says there is no such moment. Different observers would disagree about where the edge of the block is, so whose present defines the boundary? The growing block doesn't have a good answer. Another alternative is called the moving spotlight theory. This one accepts the block universe but adds something extra, a spotlight. The spotlight moves along the block, illuminating one moment at a time. That illuminated moment is the present. It's objectively real, objectively now. The spotlight moves from past to future, and as it moves, it defines what is present. This preserves the sense that the present moment is special, that right now is different from the past or the future. But it also raises questions. What is the spotlight? Is it a physical thing, a property of space-time, or just a metaphor? And if it's real, what makes it move? Why does it move at the rate it does? And again, whose spotlight are we talking about? Yours or mine? If we're moving relative to each other, our spotlights won't line up. We'll disagree about what moment is illuminated. So there's still no universal now. Every alternative to the block universe runs into the same problem. Relativity keeps insisting that simultaneity is relative, that there's no universal present. And if there's no universal present, it's hard to build a model of time that feels intuitive and also matches the physics. The block universe is the simplest solution, the most direct. It says, fine, there's no universal present, so let's stop pretending there is. All moments exist. Time is a dimension. The present is subjective, and the sense that time flows is an illusion created by the way conscious beings experience space-time. That last part, the consciousness part, is where things get even stranger. Because if the block universe is correct, then your sense of being in the present, of experiencing this moment right now, is not a feature of the universe. It's a feature of you, of how your brain processes information, of how memory and perception and awareness work. You remember the past. You don't remember the future. That asymmetry creates the sense that time is flowing from past to future, that the past is fixed and the future is open. But in the block universe, that asymmetry is not a property of time itself. It's a property of how you interact with time. The universe doesn't care which direction you call forward. It's symmetric. The arrow of time, the sense that time has a direction, comes from entropy, from the second law of thermodynamics, from the fact that systems tend to move from order to disorder. But that's a statistical tendency, not a fundamental law. And it doesn't make the future any less real than the past. Your consciousness slides along the block, experiencing one moment, then the next. But the moments themselves don't appear and disappear. They're always there. You're just not always aware of them. Think of it like reading a book. When you're on page 50, the events on page 1 still exist. They're still printed on the page. You're just not looking at them anymore. And the events on page 200 also exist, waiting for you to get there. The story doesn't come into being as you read it. It's already complete. You're just moving through it. The block universe says your life is like that book. Every moment already exists. You're just reading it one page at a time. And here's where it gets personal. If this is true, if the block universe is an accurate description of reality, then right now, as you're experiencing this moment, every other moment of your life exists too. The child you were exists. The teenager you were exists. The adult you are now exists. And the person you'll be in 10 years, 20 years, at the end of your life, that person exists too, somewhere in the block, living their moment, experiencing their present. All of those yous are real, simultaneously. And none of them is more real than any other. You think of yourself as moving through time, growing older, changing. But in the block universe, you're not moving, you're spread out. You occupy a region of space-time that stretches from your birth to your death, a four-dimensional worm, with every moment of your existence laid out along the time axis. Your past self and your future self are just different slices of the same object, the same you, frozen in the block. This is called the worm theory of personal identity, and it's exactly as weird as it sounds. You're not a three-dimensional object moving through time. You're a four-dimensional object that exists across time. And the you that's experiencing this moment is just one thin slice of that larger object. If that makes you uncomfortable, welcome to modern physics. The math doesn't care about your comfort. It just keeps pointing in this direction, toward a universe where time doesn't flow, where past, present, and future are all real. Where the present moment you feel so strongly is just your awareness sliding along a structure that already contains your entire life. And if all of that isn't strange enough, the block universe has one more implication, one that connects to the future of physics, to the next big question. If space-time is a block, a fixed four-dimensional structure, where does that structure come from? Why does it have the shape it has? Why do the laws of physics work the way they do? And is space-time itself fundamental, or is it built out of something deeper? Because the block universe, for all its strangeness, still treats space-time as the foundation, as the thing everything else sits inside. But there are hints, growing stronger every year, that space-time might not be fundamental, that it might be emergent, built out of something more basic, something that doesn't look like space or time at all. Quantum mechanics, the physics of the very small, has been pointing in this direction for decades. Particles don't have definite positions until you measure them. Entanglement links particles across distances in ways that seem to ignore space entirely. And when physicists try to combine quantum mechanics with general relativity, the math breaks. Space-time itself stops making sense at the smallest scales. The block universe gives us a picture of space-time that's strange but consistent. But quantum mechanics suggests that picture might be incomplete, that beneath the smooth four-dimensional fabric of the block, there's something else, something discrete, quantum, weird in ways that make the block universe look almost normal by comparison. And that's where we're headed next. To the place where space and time stop being smooth and continuous, where they might be woven out of quantum threads, where the block universe, for all its strangeness, might just be the surface of something far deeper. You've just been told that your entire life, past, present, and future, exists all at once in a frozen four-dimensional block. That the flow of time, the sense that right now is special, is an illusion. That you're not moving through time, you're just aware of one slice of a static structure that contains every moment you've ever experienced and ever will experience. That's uncomfortable, but at least it's coherent. The block universe fits with relativity. It explains why simultaneity is relative, why there's no universal now, why GPS works. The math holds together. The predictions match the observations. Space-time is a smooth, continuous, four-dimensional fabric, and general relativity describes how that fabric bends and curves in response to mass and energy. Einstein gave us the equations. They work. End of story. Except it's not the end of the story, because there's another theory. Another set of equations, another description of reality that's just as successful, just as well tested, and just as fundamental as general relativity. And it doesn't fit at all. The theory is quantum mechanics. And when you try to combine quantum mechanics with general relativity, when you try to describe what happens to space-time at the smallest scales or in the most extreme conditions, the math doesn't just get messy, it breaks completely. The equations spit out infinities, contradictions, nonsense. And that breakdown is telling us something profound, something that makes the block universe, strange as it is, look like just the surface of a much deeper, much weirder reality. Quantum mechanics is the physics of the very small. Atoms, electrons, photons, quarks, all the fundamental particles and forces that make up matter and energy. It's the most successful theory in the history of science by almost any measure you care to use. It explains chemistry, the periodic table, why materials have the properties they do, how lasers work, how computer chips function, why the sun shines. Every piece of modern technology, from your phone to the power grid to the medical imaging machines in hospitals, depends on quantum mechanics being correct, and it is correct, to an absurd level of precision. But quantum mechanics is also deeply, fundamentally strange. It says that particles don't have definite positions or velocities until you measure them. Before measurement, they exist in a superposition, a kind of blurred-out state where they're in multiple places at once. The act of measuring forces the particle to pick one outcome, to collapse into a definite state. But until that happens, the particle genuinely doesn't have a position. It's not that you don't know where it is, it's that where it is isn't a meaningful question. Quantum mechanics also says that particles can be entangled. Two particles can be linked in such a way that measuring one instantly affects the other, no matter how far apart they are. Not because a signal travels between them. There's no signal. The connection is immediate, instantaneous. Measure the spin of one electron, and you instantly know the spin of its entangled partner on the other side of the galaxy. Einstein hated this. He called it spooky action at a distance and spent years trying to prove it couldn't be real. He was wrong. Entanglement is real. It's been tested thousands of times. It's one of the most thoroughly confirmed predictions in all of physics. General relativity and quantum mechanics are both correct, both incredibly precise, both essential to understanding the universe, and they are completely incompatible. General relativity treats space-time as smooth, continuous, a fabric that can bend and stretch and ripple, but that exists as a definite classical structure. At every point in space-time, there's a definite curvature, a definite geometry. You can point to a location and say, this is where and when, and that location has meaning. Quantum mechanics treats everything as probabilistic, uncertain, blurred out until you measure it. And when physicists try to apply quantum rules to space-time itself, to treat the fabric of the universe as a quantum object, the math explodes. You get infinities, predictions that don't make sense, a theory that can't calculate anything useful. The problem shows up most clearly in two places: singularities and the Planck scale. A singularity is a point where the equations of general relativity break down, where the curvature of spacetime becomes infinite and the theory stops making predictions. There are two kinds of singularities that we know about: the center of a black hole, where all the mass that fell in is crushed into a point of infinite density, and the Big Bang, the moment at the beginning of the universe when all of space and time and matter and energy erupted from a single point. General relativity predicts that singularities exist. The math leads there inevitably. But physicists don't believe singularities are real in the way the equations describe them. Infinite density, infinite curvature, infinite anything is usually a sign that your theory has been pushed beyond its limits, that you're asking it to describe something it wasn't built to handle. At the center of a black hole, space-time is curved so strongly that classical general relativity stops working. You need quantum mechanics to describe what's happening at those scales, but we don't have a theory that combines them. So we don't know what actually happens at the center of a black hole. The singularity is a placeholder, a sign that says, we don't know, ask again when we figure out quantum gravity. The same thing happens at the Big Bang. Run the expansion of the universe backward in time, and general relativity says everything collapses to a point. Infinite density, infinite temperature, the entire universe crushed into a space smaller than an atom, smaller than a proton, smaller than anything. And general relativity, which works beautifully to describe the universe a fraction of a second after the Big Bang, has nothing useful to say about the moment itself. Because at that moment, at that scale, quantum effects dominate. You can't ignore them, and general relativity doesn't include them. This is where the Planck scale comes in, named after Max Planck, the physicist who helped start the quantum revolution in the early 1900s. The Planck scale is the regime where quantum effects of gravity become important, where space-time itself starts to fluctuate and blur in the same way that particle positions blur in quantum mechanics. The Planck length is about 10 to the minus 35 meters. That's a decimal point, followed by 34 zeros, and then a 1, unimaginably small. A proton is about 10 to the minus 15 meters. The Planck length is 20 orders of magnitude smaller than that. If a proton were the size of the observable universe, the Planck length would be about the size of a tree. At scales smaller than the Planck length, space-time stops being a smooth fabric. It becomes something else, something grainy, foamy, uncertain. The geometry itself fluctuates. Distances and durations stop having definite values. The neat, clean picture of space-time as a four-dimensional continuum breaks down. The Planck time is about 10 to the minus 43 seconds, the shortest interval of time that has any meaning in physics. Shorter than that, and the concept of time itself starts to dissolve. You can't ask what happened at 10 to the minus 50 seconds after the Big Bang, because there's no well-defined notion of time at that scale. The smooth ticking of the cosmic clock, the thing that lets you order events into a sequence, falls apart. This is the boundary, the edge of the map. Beyond this point, general relativity doesn't work, and we don't have a replacement. What we need is a theory of quantum gravity, a theory that combines the smooth, curved space-time of general relativity with the probabilistic, uncertain, quantized rules of quantum mechanics. A theory that can describe what happens at the center of a black hole, what happened at the Big Bang, what space-time looks like at the Planck scale. We don't have that theory yet, not a complete one, not one that everyone agrees on, but there are candidates, ideas, approaches that physicists have been developing for decades, and all of them, in different ways, suggest something radical. Space-time might not be fundamental, it might be emergent, built out of something deeper, something that doesn't look like space or time at all. One of the leading candidates is called loop quantum gravity. The idea, in its simplest form, is that space is quantized, that it's not continuous, that at the smallest scales, space is made of discrete chunks, atoms of space, tiny, indivisible units of volume that can't be subdivided further. In loop quantum gravity, the smooth fabric of space-time is an approximation, a large-scale average, like the way a sandy beach looks smooth from a distance, but turns out to be made of individual grains when you look closely. At everyday scales, at the scales where general relativity applies, space-time looks smooth because you're seeing the average of countless quantum chunks blurred together. But zoom in far enough, down to the Planck scale, and the graininess shows up. The mathematics behind loop quantum gravity is brutally complicated. It involves something called spin networks, abstract graphs, where the edges represent quantized units of area and the nodes represent quantized units of volume. These networks evolve over time, and the evolution is governed by quantum rules. The smooth space-time of general relativity emerges from the collective behavior of these networks, the same way a wave in the ocean emerges from the motion of countless water molecules. One of the striking predictions of loop quantum gravity is that the singularities might not be real. The Big Bang singularity, the infinite density at the beginning of the universe, might be replaced by a bounce, a moment where the universe was incredibly small and dense, but not infinitely so. Before the bounce, the universe might have been contracting. At the moment of maximum compression, quantum effects kicked in, stopped the collapse, and reversed it into an expansion. The Big Bang becomes the Big Bounce. This isn't science fiction. It's a genuine prediction that comes out of the math when you apply loop quantum gravity to cosmology. Whether it's correct is another question. We don't have direct evidence for a bounce. We may never have it. But the fact that the theory predicts something testable, something different from classical general relativity, is important. It means loop quantum gravity isn't just philosophy, it's physics. The other major candidate for a theory of quantum gravity is string theory. String theory takes a completely different approach. Instead of quantizing space-time directly, it changes what we think particles are. In string theory, the fundamental objects in the universe aren't point-like particles, they're tiny, one-dimensional strings, loops of energy vibrating at different frequencies. An electron isn't a point, it's a string vibrating in one pattern. A quark is a string vibrating in another pattern. A photon is a string vibrating in yet another. The properties of particles, their mass, their charge, their spin, all of it comes from the way the string vibrates. Different vibrations, different particles, and here's the key part. One of the vibrational modes of a string corresponds to a graviton, a particle that carries the gravitational force. In string theory, gravity isn't something you add on top of quantum mechanics. It's built in. It emerges automatically from the theory. That's a huge deal. General relativity and quantum mechanics don't fit together when you try to force them. But string theory unifies them by changing the rules at the foundation. The catch is that string theory requires extra dimensions, not the 3 dimensions of space and 1 of time that we experience. 10 dimensions, or 11, depending on which version of the theory you're working with. Most of those extra dimensions are curled up, compactified into shapes so small we can't detect them. But they're there, and the geometry of those extra dimensions determines the physics we observe in the familiar 4 dimensions. In string theory, space-time itself is not fundamental. It emerges from the dynamics of strings moving through a higher dimensional space. The smooth, 4-dimensional space-time of our experience is an effective description, a low-energy approximation of what's really going on at the deepest level. At high energies, near the Planck scale, the extra dimensions and the stringy nature of particles become important, and space-time stops looking like a simple 4-dimensional fabric. String theory has had enormous success as a mathematical framework. It's consistent, it's elegant. It connects to other areas of physics in surprising ways, but it also has problems. The theory makes very few testable predictions. The strings are so small, far smaller than anything we can probe with current experiments, that it's hard to know if the theory is correct. And there are something like 10 to the 500 different ways to compactify the extra dimensions, each one giving a different set of physical laws. Which one describes our universe? Nobody knows. Some physicists love string theory. They see it as the best hope for a unified theory of everything. Others are skeptical. They point out that after decades of work, string theory hasn't made a single prediction that we've been able to test. It's beautiful math, they say, but is it physics? The debate is ongoing, and it's fierce. There are other ideas too, other approaches to quantum gravity that don't fit neatly into loop quantum gravity or string theory. Causal set theory, for example, models space-time as a discrete set of events connected by causal relationships. Instead of a smooth continuum, space-time is a collection of points, like atoms, where each point represents an event. The points are connected by links that say this event can influence that event. The geometry of space-time emerges from the pattern of connections. Distance, duration, curvature, all of it comes from counting how many links you have to follow to get from one event to another. Then there's the holographic principle. This idea came out of black hole physics, from the work of physicists like Gerard Hooft and Leonard Susskind. They realized that the amount of information you can store in a region of space is limited not by the volume of the region, but by its surface area. The information content scales with area, not volume. That's strange. You'd expect that a bigger volume could hold more information, but the holographic principle says no. The maximum information is determined by the boundary, and that suggests something deep. It suggests that the three-dimensional space we experience might be a projection, a hologram. The real information, the real degrees of freedom, might live on a two-dimensional surface, and what we perceive as three-dimensional space is an emergent illusion. This has been made mathematically precise in certain contexts. In a framework called anti-de Sitter space, conformal field theory duality, physicists have shown that a theory of gravity in a higher dimensional space is exactly equivalent to a quantum theory without gravity living on the boundary of that space. Gravity and the extra dimension of space emerge from the quantum interactions on the boundary. Space itself is holographic, not fundamental. These ideas are speculative, but they're not wild speculation. They're grounded in mathematics, in calculations that work, in insights that connect to experiments, even if indirectly, and they all point in the same direction. Space and time might not be the foundation of reality. They might be emergent properties, phenomena that arise from something deeper, something more fundamental, something that doesn't look like space or time at all. This is a profound shift. For centuries, space and time were the stage, the container where physics happened. Newton gave us absolute space and absolute time. Einstein unified them into spacetime and showed that spacetime could bend. But even in general relativity, spacetime is the arena, the thing everything else sits inside. Now, quantum gravity is suggesting that spacetime itself is made of something, that it has parts, that at the smallest scales, the smooth fabric tears apart into discrete bits, quantum networks, vibrating strings, causal links, holographic projections, something. And those somethings, whatever they are more fundamental than the spacetime they build. Think about water. At everyday scales, water looks like a continuous fluid. You can pour it, swim in it, measure its temperature and pressure. But zoom in far enough, and you see that water is made of molecules, discrete particles. The smooth fluid behavior is an emergent property of countless molecules jiggling around, bumping into each other, following the laws of quantum mechanics. Nobody says water isn't real. It's obviously real. You can drink it, but the smooth, continuous nature of water is an approximation, an effective description that works at large scales but breaks down when you look closely. The molecules are what's fundamental. The fluid is what emerges. Spacetime might be like that. At large scales, it looks smooth, continuous, a four-dimensional fabric described beautifully by Einstein's equations. But zoom in to the Planck scale and the smooth fabric dissolves. What you find instead are the building blocks, the quantum bits, the strings, the loops, the causal links, the fundamental pieces that, when you put enough of them together, create the illusion of continuous spacetime. If that's true, then the questions we've been asking about space and time might be the wrong questions. We've been asking what spacetime is, how it curves, how objects move through it. But if spacetime is emergent, the deeper question is, what is spacetime made of? What are the fundamental degrees of freedom that give rise to the geometry we observe? Nobody knows, not yet. The math is hard, the experiments are harder. We can't probe the Planck scale directly. We can't build a particle accelerator powerful enough to see the graininess of spacetime or the vibrations of strings. The energies required are millions of billions of times higher than anything we can produce on Earth. But there are hints, indirect clues, observations that might point the way. The cosmic microwave background, the oldest light in the universe, carries information about the state of the universe when it was only 380,000 years old. Tiny fluctuations in the temperature of that light tell us about quantum fluctuations in the early universe, fluctuations that were stretched to cosmic scales by inflation, the brief period of exponential expansion that happened in the first fraction of a second after the Big Bang. Some versions of quantum gravity predict specific patterns in those fluctuations, patterns that might show up in the data if we look carefully enough. So far, we haven't seen them, but the searches continue. Gravitational waves, ripples in spacetime detected by observatories like LIGO, might also carry clues. If spacetime is quantized, if it has a discrete structure, that structure might leave a signature in the gravitational wave signal. A tiny deviation from the predictions of classical general relativity. Again, we haven't seen it yet, but the detectors are getting better. Black holes might be the best laboratory, because at the center of a black hole, spacetime is curved to the breaking point. If there's anywhere in the accessible universe where quantum gravity matters, it's there. We can't see inside a black hole. The event horizon blocks our view, but we can study how black holes interact with their surroundings, how they emit radiation, a phenomenon called Hawking radiation, how they merge and ring down, creating gravitational waves. Every detail we learn about black holes is a constraint on what quantum gravity can look like. And then there's the age of the universe itself, 13.8 billion years. That's the number that comes out of combining observations of the cosmic microwave background with the standard cosmological model. The Planck satellite, which mapped the microwave background in exquisite detail, gave an estimate of 13.787 billion years, accurate to within about 20 million years. That's a precision of about 0.15%, remarkably tight. That number, 13.8 billion years, is the time since the Big Bang, or, if loop quantum gravity is correct, the time since the Big Bounce. It's the age of the smooth, classical spacetime we inhabit, but it might not be the age of everything. If spacetime is emergent, if there's a deeper structure underneath, that structure might have existed before the Big Bang, before spacetime itself came into being. This is speculation, but it's informed speculation, grounded in the math. In the theories physicists are developing to extend our understanding beyond the limits of general relativity and quantum mechanics. The idea that space and time are emergent is not fringe science, it's mainstream, it's the direction the field is moving. Not because physicists want to make things complicated, because the evidence keeps pointing that way. Because general relativity and quantum mechanics can't both be right as fundamental descriptions of reality. One of them, or both of them, has to be an approximation, an effective theory that works at certain scales but breaks down at others. And when you take that seriously, when you follow the math where it leads, you end up with the possibility that spacetime is not the foundation, that the block universe, strange as it is just the large-scale structure, the emergent geometry. And beneath it, deeper down, there's something else, something that doesn't fit into our intuitions about space and time because it isn't space or time. It's the things space and time are made of, which raises a question that physics can't answer yet, but can't stop asking. If spacetime is emergent, if it's built out of something more fundamental, then what does that mean for us, for the present moment, for the sense that now is real, for the flow of time? Because if spacetime itself is an illusion, if it's just a useful approximation that emerges at large scales, then everything we've been talking about, the block universe, relativity, the bending of time and space, all of it might be surface-level description, a map, not the territory. And the territory, the actual fundamental structure of reality, might be something we can barely imagine. You've just been told that space-time itself might not be fundamental, that the smooth four-dimensional fabric Einstein described, the block universe where your entire life exists all at once, might be an approximation, a large-scale average of something deeper: quantum loops, vibrating strings, causal networks, holographic projections, something that doesn't look like space or time at all when you zoom in far enough. That's disorienting. The foundation you were standing on, the block universe with its frozen past and predetermined future, turns out to be built on something else. Something we can't see, something we don't fully understand. And if space-time is emergent, if it's constructed from pieces that aren't space or time, then what does that mean for the present moment, for now? For the sense you have, right this second, that you exist here, in this moment, experiencing this instant? The answer, uncomfortable as it is that now might not exist the way you think it does. Not universally, not objectively, not as a feature of the universe. The present moment you're experiencing, the vivid, undeniable sense that right now is real and everything else is either memory or anticipation, is not a property of space-time. It's a property of you, of how your brain processes information, of how consciousness interacts with the block universe, or the emergent quantum foam, or whatever structure reality actually has underneath. This is where physics crashes into biology, into psychology, into the hardest questions about what it means to be a conscious observer in a universe that doesn't seem to care about your experience of time. Let's start with relativity, because that's where the cracks in the universal now really show up. Special relativity already told us that simultaneity is relative, that two events happening at the same time according to one observer might happen at different times according to another observer moving relative to the first. There's no single moment, no universal present that everyone in the universe shares. But there's something deeper here, something that goes beyond the relativity of simultaneity. It's called proper time, and it's the key to understanding why your now is not my now. Proper time is the time measured by a clock that travels along a particular path through space-time. It's the time you experience, your personal duration. If you're sitting still on Earth's surface, your clock ticks. That's your proper time. If you get on a spaceship and fly away at near light speed, your clock ticks slower relative to clocks on Earth. But from your perspective, it still ticks at 1 second per second. That's still your proper time. It's always 1 second per second for you, no matter how you're moving, because you're measuring time with a clock that's at rest relative to you. But here's the thing. My proper time and your proper time don't have to agree. They don't have to line up. If we synchronize our clocks and then one of us accelerates, moves through a gravitational field, takes a trip to the edge of the solar system and back, our clocks will disagree when we meet again. We'll have aged different amounts. We'll have experienced different durations. Your now and my now will have drifted apart. And that drift isn't an error. It's not a malfunction. It's the way space-time works. Time is not a universal background ticking away the same for everyone. Time is local, personal, tied to your path through space-time. Think about the twin paradox. It's not really a paradox, but the name stuck. One twin stays on Earth. The other twin gets on a spaceship, accelerates to near light speed, flies to a distant star, turns around, and comes back. When they reunite, the traveling twin is younger, significantly younger. Not because their biology slowed down, because time itself passed more slowly for them. Fewer seconds ticked by on their clock than on the clock of the twin who stayed home. This has been tested, not with twins on spaceships, obviously, but with atomic clocks on airplanes, with particles in accelerators, with GPS satellites. Every test confirms it. Time dilation is real. Your proper time depends on your path through space-time. Now here's where it gets strange. Each twin, during the journey, has a present moment, a now, but their nows don't align. Events that are in the present for the Earth twin might be in the past or future for the traveling twin, depending on how they're moving. There's no single moment that both twins share. No universal instant where you can point and say, "This is now," for everyone, everywhere. The present moment is observer-dependent. It's a slice through space-time, and different observers slice the block universe at different angles. Your slice is not my slice. Your now is not my now. And there's no preferred slice, no correct way to cut the block that defines what's really happening right now across the universe. This is hard to accept because it contradicts something deeply embedded in human experience, the sense that there is a present moment, that right now is happening, that somewhere out there, on the other side of the planet, or on a distant star, or in another galaxy, there are events occurring right now, simultaneously with this moment, even if we can't see them. That intuition is wrong, or at least it's not supported by the physics. Relativity says there's no such thing as absolute simultaneity, no universal now. Every observer has their own present moment, and those moments don't line up unless the observers are at rest relative to each other in the same gravitational field. So why do we experience now the way we do? Why does it feel so undeniably real, so vivid, so obviously the only moment that exists? The answer is biology, evolution, the way your brain is wired. You are not designed to perceive space-time accurately. You're designed to survive, to navigate a world of predators and prey, food and threats, social alliances and dangers. And for that, you need a model of reality that's simple, fast, and good enough. Not accurate, good enough. Your brain constructs a model of the present moment by integrating sensory information over a brief window of time, roughly a few hundred milliseconds. Shorter than that, and you can't process it. Longer than that, and the information is too old to be useful. So your brain stitches together sights, sounds, touches, smells, all arriving at slightly different times from different sources, and presents them to your conscious awareness as a single unified now. That now feels instantaneous. It feels like a single moment, but it's not. It's a composite. A constructed snapshot built from data that arrived over a span of time. Your brain smooths out the delays, synchronizes the inputs, and gives you the illusion of a present moment. This is useful. If you're a hunter chasing prey or an animal fleeing a predator, you don't need to know that the light from the prey's body took a few nanoseconds longer to reach your eyes than the sound of its footsteps took to reach your ears. You need to know where it is now, or at least where your brain's best guess says it is, so you can act fast, without thinking. The present moment you experience is a tool, a cognitive shortcut. It's not a feature of the universe, it's a feature of you. And here's the kicker. Your experience of time flowing, of moving from past to future, is also constructed. It's not something you perceive directly. You don't have a sense organ for time the way you have eyes for light or ears for sound. What you have is memory. You remember the past. You don't remember the future. And that asymmetry creates the sensation of time flowing in one direction. But that asymmetry is not built into the laws of physics, not fundamentally. The equations of motion, whether you're using Newton's laws or Einstein's relativity, or even quantum mechanics, work just as well running backward in time as forward. If you film a planet orbiting a star and play the film in reverse, the motion still obeys the laws of physics. There's nothing in the equations that says time must flow forward. The arrow of time, the sense that past is different from future, comes from thermodynamics, from the second law, from the fact that entropy, a measure of disorder, tends to increase over time. Systems move from order to disorder. Eggs break, coffee cools, rooms get messy. And that process is irreversible, not because the laws of physics forbid it, but because the reverse process is statistically unlikely. You could, in principle, have all the air molecules in a room spontaneously gather in one corner. The laws of physics allow it, but the odds are so astronomically low that it never happens. Entropy increase gives time a direction. It creates a distinction between past and future. Low entropy in the past, high entropy in the future. And your brain, your memory, your sense of causality, all of it is built on that distinction. You remember low entropy states, the past, because memories are physical structures in your brain that can only form when entropy is increasing. You can't remember the future because memory formation is an entropy increasing process that points backward in time. So the flow of time, the present moment, the sense that now is special, all of it is a consequence of how you interact with the universe, not a property of the universe itself. The block universe doesn't flow, it doesn't have a present, it just is, a static four-dimensional structure. And you, moving through it, or experiencing slices of it, or whatever metaphor works best, are constructing the sensation of time passing because that's what your brain evolved to do. This is deeply unsettling. It means that the most immediate, most undeniable aspect of your experience, the fact that you are here, now, experiencing this moment, is not something the universe recognizes. There is no cosmic now, no universal present. Just a collection of observers, each with their own proper time, their own slice through space-time, their own constructed present moment that doesn't align with anyone else's. And if the block universe is itself emergent, if space-time is built out of quantum bits or strings or causal links, then even the notion of a four-dimensional structure might be an approximation. The territory beneath the map might not have anything resembling time at all, just quantum states. Entanglements, correlations, information, and the smooth flow of time we experience is something that emerges at large scales when you average over countless quantum events. There's a way to make this more concrete. Think about what happens when you look at a star. The light you're seeing left that star years ago, decades ago, centuries ago, depending on how far away it is. When you look at the Andromeda galaxy, you're seeing light that left 2.5 million years ago. You're not seeing Andromeda as it is now. You're seeing it as it was in the deep past. But here's the question: what does now mean for Andromeda? If you're on Earth and you say, "I wonder what's happening on Andromeda right now," what are you asking? You're asking about events in Andromeda that are simultaneous with your present moment. But simultaneity is relative. An observer moving relative to you would draw a different slice through space-time and pick out a different set of events in Andromeda as simultaneous with your present. There's no single answer to the question, what's happening on Andromeda right now? The question doesn't have a unique meaning. It depends on your reference frame, on how you're moving, on where you are in space-time. This gets even weirder when you think about distant galaxies. Galaxies billions of light years away. When you look at them through a telescope, you're seeing light that's been traveling for billions of years. You're seeing those galaxies as they were when the universe was young, when the Earth didn't exist, when the sun hadn't formed. But those galaxies still exist, presumably, in some present moment. Except there's no single present moment that includes both you and those galaxies. Your now and their now are separated by billions of years of light travel time, and there's no objective way to synchronize them. You can pick a definition. You can say, let's define simultaneity using this reference frame. But it's a choice, a convention, not a fact about the universe. This is what relativity does to the concept of now. It dissolves it. It turns it into something observer-dependent, frame-dependent, a slice through space-time that has no universal significance. And if space-time itself is emergent, if it's built from something deeper, then even the slices might be approximations, useful fictions that work at large scales but break down when you look closely. So where does that leave consciousness, the thing that's actually experiencing now? The thing that's reading these words or hearing this voice and feeling undeniably that this moment is real? Physics doesn't have a good answer. Consciousness is not part of the equations. It's not a term in the Einstein field equations or the Schrödinger equation or the standard model of particle physics. It's not something physics knows how to describe. Some physicists think consciousness is irrelevant to the fundamental structure of the universe, that it's an emergent property of complex systems, brains, neural networks, information processing. That consciousness arises when a system becomes complicated enough to model itself, to represent its own states, to distinguish between past and future, and construct a sense of self. And once you have that, once you have memory and anticipation and a model of the world, you get the sensation of time passing, the experience of now. But it's all emergent, built on top of the physics, not part of the foundation. Other physicists are less sure. They point out that consciousness is the only thing we experience directly. Everything else, every observation, every measurement, every piece of data comes to us through consciousness. We don't observe the universe directly. We observe our experience of the universe. And that experience is structured by time, by causality, by the sense that events happen in sequence. If space-time is emergent, if it's not fundamental, then maybe consciousness is part of the mechanism that builds it. Maybe the reason we experience time flowing is because the act of observing, of being conscious, is what selects a particular slice through the block universe. What collapses the quantum superposition? What creates the distinction between past and future? This is speculative, way beyond what the current physics can say, but it's a direction some researchers are exploring. The idea that consciousness and space-time are connected, that the observer and the observed are not separate, that the universe doesn't have a structure independent of the act of observing it. This connects, loosely, to the multiverse, to the idea that there are many universes, many branches of reality, each with its own structure. And in some interpretations of quantum mechanics, every time a quantum event happens, every time a particle is measured or a wave function collapses, the universe splits. One branch where the particle is here, another branch where it's there, and both branches are real, both exist. You just happen to be in one of them. If the multiverse is real, and that's a big if, then each branch has its own version of space-time, its own four-dimensional block, its own set of observers with their own present moments. Your now exists in this branch. But there's another you in another branch experiencing a different now, a different sequence of events, a different slice through a different block universe. And if space-time is emergent in each branch, if it's built from quantum bits or strings or whatever the fundamental stuff turns out to be, then each branch might have a different structure, a different geometry, a different set of rules for how space and time behave. The multiverse isn't just many universes, it's many spacetimes, many different ways for reality to be structured. This is where the physics gets speculative enough that most scientists hedge their language carefully. The multiverse is not an established fact. It's a prediction of certain interpretations of quantum mechanics and certain models of cosmology. Eternal inflation, for example, the idea that the universe is constantly spawning new regions of space, each with its own local physics, predicts a kind of multiverse. So does the many worlds interpretation of quantum mechanics. But neither one has been confirmed. We don't have direct evidence that other branches or other universes exist. We might never have such evidence. Some versions of the multiverse are in principle unobservable, so why talk about it? Because it's a logical consequence of taking the math seriously. If quantum mechanics is correct, and it is, and if the wave function doesn't collapse but instead evolves into a superposition of all possible outcomes, then you end up with many worlds. If inflation is correct, and the evidence is strong, and if it's eternal, meaning it never stops in some regions, then you end up with a multiverse of pocket universes. The math leads there. Whether nature follows the math all the way is an open question. But here's what's relevant for the concept of now. If the multiverse is real, then the present moment is even less universal than relativity already suggested. It's not just observer-dependent within one universe. It's branch-dependent across the multiverse. Every version of you, in every branch, has their own now, their own experience of the present, and none of them is more real than any other. This is the ultimate dissolution of the universal present, not just relative within spacetime, not just emergent from quantum foam, but multiplied across countless branches, countless universes, each with its own structure, its own flow, its own set of conscious observers experiencing their own nows. And through all of this, through relativity and quantum mechanics and the block universe and emergent spacetime and the multiverse, one thing stays constant: your experience. The fact that you are here, now, reading this, or hearing this, or thinking about this, that experience is real. Undeniably real. It's the one thing you can't doubt. The one thing that doesn't go away, no matter how strange the physics gets. Descartes said it in Latin: cogito ergo sum, I think, therefore I am. The act of experiencing, of being conscious, is proof that something exists. You might be wrong about what you're experiencing. You might be wrong about the structure of space-time, or the nature of time, or whether the block universe is real. But you can't be wrong about the fact that you're experiencing something. That experience is tied to time, to the sensation of moments passing, to memory and anticipation, and the flow from past to future. And that flow, that sensation, is built into the way you interact with the universe. It's not separate from you. It's not something you observe from the outside. It's woven into your existence. Which means that even if space-time is emergent, even if the block universe is an approximation, even if the multiverse is real and there are countless other yous experiencing countless other nows, your now still matters. It's real for you. It's the only thing you have direct access to. And in some deep sense, it's the only thing that is real, because reality, whatever it is at the fundamental level, only becomes experience through the act of observing, through consciousness, through you. This is not solipsism. It's not saying that only your mind exists and everything else is illusion. The universe is real. Space-time is real, or at least it's a very good approximation. The laws of physics are real. Other people are real. Other observers are real. But all of it, every bit of it, comes to you through the filter of your consciousness, through your experience of now, and that experience is shaped by biology, by evolution, by the fact that you're a human being with a human brain that evolved to navigate a world of medium-sized objects moving at medium speeds, not a world of quantum superpositions or relativistic time dilation or emergent space-time. Your brain wasn't designed to understand the universe at the level physics describes. It was designed to keep you alive long enough to reproduce. And for that, a simple, intuitive model of time works fine. But now, 13.8 billion years after the Big Bang, after the universe expanded and cooled and formed stars and planets, and eventually life, and eventually humans, with big brains and curiosity and the ability to do math, you're in a position to ask questions that evolution never prepared you for. What is time? What is now? Is the future real? Is the past gone? and the answers physics gives don't match the intuitions biology gave you. That's not physics being wrong, that's biology being limited. Your intuitions are good enough for everyday life, but they're not good enough for the edges of reality. For black holes and the Big Bang and the Planck scale. For the places where space-time bends or breaks or dissolves into something else. And here's the deepest, strangest part. You are made of space-time. Not in a poetic sense, in a literal sense. Your body, your brain, every atom in your cells exists in space-time, moves through space-time, is shaped by space-time. The curvature of space-time near Earth is what holds you to the ground. The flow of time through your neurons is what creates the experience of consciousness. You are not separate from the fabric of the universe. You are part of it, a localized pattern of matter and energy moving through a four-dimensional structure, or an emergent approximation of such a structure, experiencing a sequence of moments, because that's what patterns like you do. You are space-time aware of itself, a region of the block universe complex enough to construct a model of its own existence, to ask questions, to wonder, to experience now. And that brings us to the final question, the one that physics can describe but can't fully answer. If you are part of space-time, if your existence is woven into the fabric of the universe, then what does that mean for who you are, for your place in reality, for the fact that you're here, now, asking these questions at all? That's where we're going next. To the place where the physics and the philosophy and the lived experience come together, where the abstract structure of the block universe meets the concrete fact of your existence, where the deepest insights about space and time turn into insights about what it means to be human, to be conscious, to be alive in a universe that's far stranger, far more beautiful, and far more interconnected than anyone imagined before Einstein sat down and started thinking about light. You've been told that space-time might be emergent, that the present moment is observer-dependent, that the flow of time, the vivid sensation that right now is the only moment that exists, is a construct, a trick your brain plays because evolution built you to survive, not to understand the universe at its deepest level. You've been told that past, present, and future might all exist simultaneously in a four-dimensional block, that your entire life, from birth to death, is already laid out in the fabric of space-time, frozen, unchanging, like frames on a film strip. And if that wasn't strange enough, you've been told that the block itself might not be fundamental, that space-time could be built from something deeper. Quantum bits, vibrating strings, causal links, something that doesn't look like space or time at all when you zoom in far enough. That's a lot to absorb. And if you're feeling unmoored, like the ground has been pulled out from under you, that's appropriate, because the ground has been pulled out. The comfortable, intuitive picture of reality, the one where space is a container and time is a river flowing steadily from past to future, that picture is gone. It lasted from Newton to Einstein, 218 years, long enough to feel permanent, but it wasn't permanent. It was an approximation, a useful fiction that worked at everyday scales but broke down when you looked closely enough. What replaced it is far stranger. Space-time isn't a stage where events happen. It's a dynamic, flexible, four-dimensional fabric where space and time are woven together, where gravity is geometry, where your motion affects the passage of time, where simultaneity is relative, where the present moment depends on your reference frame. And beneath all of that, at the smallest scales, the fabric might dissolve into something that doesn't resemble space or time at all. This is where we are, 13.8 billion years after the Big Bang, or 13.787 billion if you trust the Planck satellite's measurement. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, and the light released at that moment, stretched and redshifted by billions of years of cosmic expansion, is now the cosmic microwave background, the oldest light we can observe. A snapshot of the universe as it was when it was a fraction of its current age. That light has been traveling for over 13 billion years to reach us. And when we map it, when we measure the tiny fluctuations in its temperature across the sky, we can reconstruct the conditions of the early universe with extraordinary precision. We know the universe is about 13.8 billion years old. We know it's made of roughly 68% dark energy, 27% dark matter, and 5% normal matter. We know it's expanding, and that expansion is accelerating. We know all of this to within a few percent, but knowing the numbers doesn't answer the deeper question, the one that physics can describe but can't fully resolve. What does all of this mean for you? For the fact that you're here, now, experiencing this moment, asking these questions. That's what this final piece is about, not the math, not the measurements, the implications, the shift in perspective that happens when you take the physics seriously and follow it all the way through to what it says about your place in the universe. Start with the obvious. You are made of atoms. Carbon, hydrogen, oxygen, nitrogen, a few dozen other elements scattered through your cells in trace amounts. Those atoms were forged in stars, literally. The hydrogen in your body is primordial, left over from the Big Bang. But everything heavier than hydrogen, every carbon atom in your DNA, every calcium atom in your bones, every iron atom in your blood, was created in the core of a star that lived, burned through its fuel, and exploded in a supernova billions of years ago. You are stardust. That's not poetic exaggeration, that's chemistry. The atoms in your body are older than the Earth, older than the Sun. They've been recycled through countless stars, scattered across the galaxy, pulled together by gravity into the cloud that became the solar system, condensed into the planet you're standing on, incorporated into life, passed through ecosystems, and eventually assembled into the specific arrangement that is you. Every breath you take contains atoms that were once part of other living things, trees, animals, humans. The carbon dioxide you exhale will be absorbed by a plant, turned into sugar, eaten by something else, passed along. Your atoms are temporary, on loan, borrowed from the universe for the span of your life, then returned. The matter that makes up your body has been around for billions of years and will continue to exist long after you're gone. But you, the pattern, the specific arrangement of those atoms, the structure that thinks and feels and experiences, you are temporary. You're a configuration, a process, a wave moving through the ocean of matter and energy that fills the universe. Now add relativity. You're not just made of atoms. You're made of space-time. That sounds abstract, but it's not. Your body exists in space. It occupies a volume. You can measure it. You're about 1.5 meters to 2 meters tall, depending. You weigh somewhere between 50 and 100 kilograms, depending. You take up space. You have a location. Right now, you're here. Wherever here is for you. But you also exist in time. You have a duration. You were born on a specific date. You'll die on a specific date. The span between those two moments is your lifetime. And just as your body occupies a volume in space, it occupies an interval in time. From the perspective of the block universe, you're not a three-dimensional object moving through time. You're a four-dimensional object that extends from your birth to your death, a space-time worm. A world line stretching through the block. Every moment of your life is a slice through that four-dimensional structure. The you that's reading this right now is one slice. The you that was born is another. The you that will die is another. And all of those slices exist simultaneously, not in the sense that they're all happening at the same instant, because there is no universal instant, but in the sense that they're all part of the block. All part of the structure of space-time. This is not how you experience yourself. You experience yourself as existing in the present, as moving forward through time, as having a past that's gone and a future that hasn't happened yet. But that experience is a perspective, a point of view. The conscious you, the experiencing you, is aware of one slice of the space-time worm at a time. You're sliding along your world line, moment by moment, experiencing the sequence as it unfolds. But the world line itself is already there, complete, from birth to death. If that feels uncomfortable, if it feels like it strips away your agency or your free will, or the sense that your choices matter, sit with that discomfort for a second, because the block universe doesn't say your choices don't matter. It just says they're part of the structure. The decisions you make, the actions you take, the paths you follow, all of it shapes your world line. The fact that the world line exists doesn't mean you didn't choose it. It means the choosing is part of the block. Think of it this way: you're reading this right now. That's a fact, a moment in your world line. In a few minutes, you'll finish reading or listening, and you'll move on to something else. That future moment also exists in the block, but it exists because of the choices you're making now. The decision to keep reading, the decision to engage with this material. The path from this moment to that moment is shaped by your actions. The block contains the result, but you're the one creating the path. This is the philosophical shift, from thinking of yourself as moving through space-time to recognizing that you are space-time. Or at least, you're a pattern in space-time, a localized disturbance, a configuration of matter and energy that's complex enough to be aware of itself, to construct a model of the universe, to ask questions. Your brain, the 3 pounds of grey matter sitting inside your skull, is a space-time object. It exists in 4 dimensions, just like everything else, and the processes happening inside it, the firing of neurons, the flow of electrochemical signals, the patterns of activation that give rise to thoughts and memories and emotions, all of that is happening in space-time. Your consciousness is not separate from space-time, it's embedded in it. It's part of the structure, and here's where it gets even stranger. If space-time is emergent, if it's built from something deeper, then you are also emergent. You're not just a pattern in space-time. You're a pattern that emerges when quantum interactions become complex enough to form atoms, molecules, cells, brains. You're the large-scale structure built from countless tiny quantum events happening at the Planck scale, averaged out, smoothed over, organized into the coherent classical object you experience as your body. You are, in a very real sense, a bridge between the quantum and the classical, between the microscopic world where particles exist in superposition and the macroscopic world where objects have definite positions. Your existence depends on both. You're built from quantum parts, but you behave classically. You have a location, a trajectory, a world line. The quantum fuzziness averages out when you zoom out to human scales, and what's left is you. Solid, definite, real. But the quantum stuff is still there, underneath. Every atom in your body is a quantum object. Every chemical reaction in your cells involves quantum mechanics. The bonds between molecules, the transfer of energy, the replication of DNA, all of it depends on quantum effects. You are quantum at the bottom and classical at the top. A multi-layered structure that spans from the Planck scale to the human scale. And all of that, the quantum foundation, the classical emergence, the space-time structure, the 4-dimensional world line, all of it is you. Not separate pieces, one integrated whole. You can't draw a clean line between where the universe ends and where you begin, because there is no such line. You're not in the universe like a marble in a box. You're part of the universe, made of the same stuff, following the same laws, shaped by the same forces. Gravity, the curvature of space-time, caused by the mass of the Earth, is what holds you to the ground. Electromagnetism, the force between charged particles, is what holds your atoms together, keeps your molecules intact, lets your neurons fire. The strong nuclear force holds the protons and neutrons in your atomic nuclei together. The weak nuclear force governs the radioactive decay that powers the sun, which powers photosynthesis, which powers the food chain, which powers you. You are not separate from these forces. You are an expression of them. A temporary, localized configuration that exists because the laws of physics allow it. Because the universe, after 13.8 billion years of expansion and cooling and structure formation, reached a state where matter could clump into stars, where stars could forge heavy elements, where those elements could form planets, where planets could harbor life, where life could evolve complexity, where complexity could produce consciousness. You are the universe's way of knowing itself. That's not mysticism, that's just a description of what you are. A region of space-time where matter has organized itself into a pattern complex enough to perceive, to think, to reflect. You look out at the stars and ask where they came from. You measure the cosmic microwave background and calculate the age of the universe. You build telescopes and particle accelerators and satellites. You write equations, you test predictions, you refine your understanding. And every time you do that, every time you learn something new about the cosmos, you're not discovering something external. You're discovering something about yourself, because you're made of the same stuff. The carbon in your body was forged in the same stellar furnaces that forged the carbon in distant galaxies. The forces shaping the universe are the same forces shaping you. The laws of physics that govern the motion of planets also govern the firing of your neurons. There's no separation, no boundary. You are not an observer standing outside the universe looking in. You are the universe looking at itself. This is the deepest implication of taking space-time seriously. The shift from thinking of yourself as separate to recognizing that you're integrated, woven into the fabric, part of the structure. Your existence is not an accident or an anomaly. It's a natural consequence of the laws of physics playing out over billions of years in a universe that started hot and dense and has been expanding and cooling ever since. The block universe says your entire life exists, all at once, as a four-dimensional object. But you don't experience it all at once. You experience it one moment at a time, sliding along your world line, aware of the present, remembering the past, anticipating the future. That experience is real. It's what it's like to be a conscious observer embedded in space-time. And if space-time is emergent, if it's built from quantum bits or strings or something else, then your experience of time, the flow from past to future, the sense that now is special, is part of the mechanism that constructs space-time. Your awareness, your observation, your consciousness might not be separate from the physics. It might be part of what makes the physics work, part of what selects a particular branch of the wave function, part of what creates the distinction between past and future. This is speculative, way beyond what current physics can confirm, but it's a possibility worth sitting with. The possibility that consciousness and space-time are connected, that the observer and the observed are not separate, that the universe doesn't have a structure independent of the beings inside it who are capable of measuring, thinking, experiencing. If that's true, then you're not just part of space-time, you're part of what makes space-time what it is. Your existence contributes to the structure. The fact that you're here, now, experiencing this moment, is not incidental, it's fundamental, built into the fabric of reality at the deepest level. This changes the question of meaning. People ask, what's the point? Why are we here? What's the purpose of existence? And physics doesn't answer those questions. Physics describes how things work, not why they work or what they're for. Physics is silent on meaning. But recognizing that you are part of space-time, That you're not separate from the universe but integrated into it, shifts the frame. You're not looking for meaning from outside. You're not waiting for the universe to tell you what the point is. You are the point. Your existence, your experience, your awareness, that's what gives the universe the ability to ask the question in the first place. The universe, for most of its history, was a hot, dense fog of particles. No stars, no planets, no life, no consciousness. Just matter and energy following the laws of physics, expanding, cooling, clumping together under gravity. It took hundreds of millions of years for the first stars to form, billions of years for planets to appear, billions more for life to evolve, for complexity to build, for brains to develop, for consciousness to emerge. And now, 13.8 billion years later, a tiny fraction of the matter in the universe has organized itself into structures capable of thinking, of wondering, of asking what the universe is and where it came from and what it means to be alive inside it. That's not common, that's rare, extraordinary, unlikely. And yet here you are the universe's way of experiencing itself. The universe doesn't care, in the sense that it's not conscious, not purposeful, but you care, you experience, you feel, you think, and that caring, that experience, is part of the universe too. It's not separate, it's embedded in the structure. A natural consequence of the laws of physics creating complexity. So when you look up at the night sky, when you see the stars scattered across the darkness, remember that you're looking at the same stuff you're made of, the same atoms, the same forces, the same space-time. You're not separate from what you're seeing. You're continuous with it, connected to it, part of it. And when you feel time passing, when you notice the present moment slipping into the past and the future rushing toward you, remember that this sensation is not something the universe imposes on you. It's something you construct, a perspective, a slice through the block universe. The flow of time is real for you, even if it's not a feature of space-time itself, because you are real. Your experience is real. And the fact that you're here, now, experiencing this moment, is the most undeniable, unquestionable thing you have access to. Descartes was right. I think, therefore I am. The act of experiencing proves existence. And your existence, strange as it is, temporary as it is part of the larger structure of space-time. You're a four-dimensional object, a world line stretching from birth to death, a pattern of matter and energy complex enough to be aware of itself, to ask questions, to wonder. And here's the beautiful part, the part that makes all of this worth thinking about. The universe is stranger, more interconnected, more beautiful than anyone imagined before Einstein sat down and started thinking about light, before Planck discovered quantization, before Hubble saw the galaxies receding, before the cosmic microwave background was measured, before general relativity and quantum mechanics and particle physics and cosmology all came together to give us a picture of reality that's so far removed from everyday intuition that it feels like science fiction. But it's not fiction, it's real, tested, confirmed. The predictions match the observations. GPS works because relativity is correct. Atomic clocks tick at different rates depending on gravity and speed. Particles in accelerators live longer when they're moving fast. Gravitational waves ripple through space-time when black holes collide. The cosmic microwave background glows at 2.7 Kelvin, exactly as predicted by the Big Bang model. All of it works, all of it fits together, and all of it points to a universe that's far more unified, far more deeply connected than the Newtonian picture suggested. Space and time aren't separate. Mass and energy aren't separate. Matter and space-time aren't separate. You and the universe aren't separate. This is the philosophical shift that comes from taking modern physics seriously. From moving beyond the intuition that you're a separate observer standing outside the universe looking in. You're not outside, you're inside. You're part of the structure. And recognizing that, fully internalizing it, changes how you see yourself, how you see your place in the cosmos, how you understand your connection to everything else. You are space-time, not in some vague metaphorical sense, in a literal physical sense. Your body occupies a region of space-time. Your world line extends through the block universe. Your existence emerges from quantum interactions at the smallest scales, smoothed out into the classical object you experience as yourself. You are a temporary pattern in the fabric of reality, a configuration of matter and energy that exists for a brief interval, measured in decades, in a universe that's existed for billions of years and will continue to exist for trillions more. That's humbling. You're small, temporary, fragile, a brief flicker of awareness in an unimaginably vast cosmos. But it's also empowering. Because you're not insignificant, you're part of the structure, you're made of the same stuff as stars, you're shaped by the same forces that govern galaxies. You're connected through the fabric of space-time to everything that has ever existed and everything that ever will exist. Your atoms were forged in stars. Your awareness is a consequence of the laws of physics. Your experience of time is a perspective on the block universe. Your consciousness is the universe's way of knowing itself. You are not separate. You are integrated, woven into the fabric, part of the story. And that story, the story of the universe, is still being written, still unfolding, still evolving, and you're part of it, right here, right now. In this moment, this slice of the block, this point on your world line, this experience of being alive, of being conscious, of being aware that you exist. That experience is real. It's all you have. It's all anyone has. And it's enough, because it's woven into the deepest structure of reality, into space-time itself, into the fabric of existence. You are space-time, and space-time is you. And recognizing that, fully embracing it, is the final step in understanding what it means to exist in a universe that's far stranger, far more interconnected, and far more beautiful than anyone ever imagined. You've just spent the last hour learning that everything you thought you knew about space and time is wrong. Not a little wrong, fundamentally, completely, almost insultingly wrong. Space isn't a container. Time isn't a river. The present moment isn't universal. The flow from past to future is a trick your brain plays because evolution cared more about keeping you alive than teaching you physics. And beneath it all, beneath the smooth fabric of space-time that Einstein described, there might be something else entirely. Quantum bits, vibrating strings, causal links, something that doesn't look like space or time at all. That's disorienting. It should be, because what you're being asked to accept is that reality at its deepest level does not resemble reality as you experience it, not even close. The intuitions you've relied on your entire life, the sense that you're here, now, moving forward through time, those intuitions are useful fictions, approximations that work at human scales but break down when you look too closely. And yet, none of this makes your experience less real. The fact that the present moment is observer-dependent doesn't mean the present moment doesn't exist for you. The fact that your entire life might be laid out in a four-dimensional block doesn't mean your choices don't matter. The fact that space-time might be emergent doesn't mean you're not part of it. You are, deeply, inextricably. You're not separate from the fabric of the universe. You're woven into it, made of it, shaped by it. Every atom in your body was forged in a star. Every force holding you together is the same force holding galaxies together. Every moment you experience is a slice through a structure that contains everything that has ever happened and everything that ever will. You are not standing outside the universe looking in. You are the universe looking at itself. 13.8 billion years of cosmic evolution concentrated into a pattern complex enough to wonder where it came from. That's what you are. Not a separate observer, a participant. An expression of the laws of physics playing out in a corner of space-time that happened to produce stars, planets, life, consciousness, you. Keep asking, because each new measurement may not simply reveal the universe's contents, but the hidden rules that let reality unfold.